My name is Richard Ferrer, and I can say I am cloud hired.
That yes, come and join and get cloud hired. I'm cloud hired.
I'm cloud hired.
I'm cloud hired.
Hey, Go Cloud Architect family, I'm cloud hired.
So I'm cloud hired, guys.
So I'll just say I'm cloud hired.
I'm cloud hired.
I'm cloud hired thanks to Go Cloud Architects.
It worked for me, and now I'm cloud hired. Because of Google Architect program, I am cloud hired. See!
I am cloud hired. Thank you, Mike and the GlowCloud team.
Welcome back, everyone. Leo and I are back for day 5 of the completely free Google Professional Cloud Architect Bootcamp. Actually, this is day 6 to help you prepare for the Google Professional Cloud Architect certification and the Google Professional Cloud Architect exam. My name's Mike Gibbs. I'm here hosting this session along with Leo Paredes. I'm in South Florida. Leo's in Sao Paulo, Brazil today, and we have a big day outlined for you. So if you just joined us, if you just heard out about it, don't worry. I want to let you know that you can go back and work the previous 5 days. Chris from my team is going to give you the playlist for all those videos so you can catch up. You can attend today and then go back for the rest. If you just joined us, I want to let you know that we have a study guide, this nice 550-page study guide my team wrote to help you pass the exam to go along with this boot camp and sign up. It'll be emailed to you within 10 to 15 minutes, and you can use that to follow along to prepare for the Google Professional Cloud Architect certification and to use it as a guide. So please download that. I also want to remind you that this Thursday, like every Thursday, we will have a how to get your first cloud architect job. We will talk about the system that I created 25 years ago, which is what you need to use when you get your first tech job. I've gotten people hired at Apple, Amazon, Cisco, Google, IBM, Accenture, Deloitte, KPMG, Capgemini, PricewaterhouseCoopers, Barclays Bank, JP Morgan Chase Bank, any company you can think of, honestly. We'll talk about what it takes to get hired, what the skills that you need to be an architect, how you stand out, how you get interviews, how you bypass HR, and everything you need to do to get your first cloud architect job. It's free. We'll talk for about 30, 45 minutes, and then we'll answer any questions. You want to see if you're ready and you want a mini cloud architect interview? I'll tell you whether you're ready or not right then and there. Want to validate your skills? I'll validate your skills. Want me to check your LinkedIn profile and see if it looks like an architect versus an engineer? I'm happy to do it, and it's all free on this once-a-week webinar. This week, we'll do it at 11 a.m. 11 a.m. because we have the boot camp. So sign up. Chris from my team will drop that link. And then let's start thinking about passing this Google Professional Cloud Architect exam. So the flow today is going to be as follows. We're going to talk about compute and containers for about 45 minutes. Then Leo's got about 5 labs that we're going to go through, and Leo can tell you what they are in a minute. Then we're going to talk a little bit about storage. So this is going to be a fun day. Leo, you want to talk to people about the 5 labs that you have that are coming after the first lecture and what they're going to be?
Sure, Mike. We have labs demonstrations about creating custom image to boot virtual machines, how to create instance templates, how to create instance templates from existing virtual machines, how to create managed instance groups, and how to use auto-scaling when using managed instance groups.
So that sounds fun, Leo. Okay, so I want to know that you're awake, you're alert, you're oriented, that you're going to be here and be present. So do 2 things for me. Please tell me where you're at with your ad in the chat box. I am in Port St. Lucie, Florida right now. Tell me where you're at. And then once I know where you're at, give me a hashtag Google Professional Cloud Architect, because that way I know what you're here for. I know what you're thinking, and I know everybody is awake. As soon as we see a few of those come in, we will begin with the content, because we've got a very eventful today and a week for you. So Hector, you're in New York. I love that. Adrian, Google Professional Cloud Architect. I love it. Well communicated, Adrian. Thank you. San Jose, T-Folio. I used to fly out to Tasman Drive almost every week. Little Rock, Arkansas. I've actually never been there, but always wanted to. Middleton, New York. I've spent a lot of time with. A lot of time out there. Louisiana, I've actually spent a lot. How close is that to New Orleans? I've spent a lot of time in New Orleans. Cisco Live used to be there all the time. Lots of time in that area. Chicago, Darnell, I used to go out there all the time. Loved the Equinox. I think it was not Miracle Mile. It was a really great gym for me to work out because I like to work out. Ahmed's over there in Kingdom of Saudi Arabia. I haven't been there in a while, but I used to spend a lot of time in that part of the world. Always loved it. Spent great time in Saudi Arabia, great time in Dubai, lots of great times over there. All right. Well, Chris, it looks like people here are awake, they're alert and oriented. We'll go with the first lecture. And then after, though, and Chris picked it up exactly. I am not great with French words, so I intentionally tried to skew right over that one. Apologies. He is absolutely right, Chris, on that one. Now, if it's Greek, now we know we're talking another language. That makes sense to me. All right, Chris, let's roll with the content.
Okay, let's talk about containers. So we're going to begin with what is a container. A container is going to be a standardized unit of software packaging that basically is going to be the application and its dependencies. And the key with a container is it contains everything that's needed to run, except the underlying operating system components. So containers are very portable. So imagine taking a box, putting something into it, and shipping it somewhere else. That's the way I view the container, is we're putting the application, we're putting its dependencies in a single self-contained environment, and then we can move that anywhere we want. So that's going to be the container. And I'm going to show you in a document and a diagram I made in a minute to try to help make it easier. But that's what we're really talking about. Packaging up the application and its dependencies, and then shipping it off to go run on another server that's designed to run containers. Now, when it comes to containers, there's two parts of it. There's the orchestration of it, which is the control plane that determines how many containers are running and things like that. And then there is the data plane, which is where the work is done. So let's talk about how this works together. So in a traditional architecture, and this would work, by the way, in any data center or any cloud, we typically have we have a control plane. And this exists for everything. We have a control plane for the network, typically the routing protocols. In a software-defined networking, we've got separation between where the routers, the forwarding capabilities, and the control plane, which is somewhere else. And the control plane is going to determine the number of containers. Now, the containers have to work somewhere. So no matter what you hear, containers are always going to be running on a server. Now, either they're going to be running on a provider's environment that's going to look like I show you, or this is going to be your own environment. It doesn't matter. It's all going to be used on something like this. And the way this is going to work is we typically have our servers, and we typically put containers on virtual machines. We could also put them in the bare metal server itself. So it could go either way, but typically virtual machines are pretty easy to manage. So we might have a server, we might smack a hypervisor on it, we might create a giant virtual machine with a whole bunch of CPU cores and a whole bunch of DRAM. And then we may install a container runtime module on it, like Docker, that enables the containers to run. And then we will have these little things called the container. Now, the reason I'm moving this thing around is this thing is portable. So If I have an application that's designed to run for Linux, this virtual machine is already Linux, so I already have that Linux kernel here, and whatever is necessary from the operating system for this container to use. And now what I have here is I've got my application, which is the code the developer wrote, and the dependencies or whatever that application needs. Any operating system libraries I need, I'm borrowing it directly from this container, from this virtual machine. And this container runtime module is like a hypervisor for an operating system, which logically isolates this virtual machine versus this virtual machine, where this hypervisor here is isolating virtual machine from virtual machine on that same physical server. The container runtime is really what's helping you isolate these containers from each other and allowing them to run separately in a secure, isolated environment. Containers will run off of container images, which will be considered a read-only snapshot that will define the environment that the container is used. Kubernetes can handle all of this now, but you often see this environment of Kubernetes doing the control plane and Docker being the container runtime module. So let's talk about Kubernetes. So we, realistically speaking, have two options. Option one, we manage our entire Kubernetes cluster. Now, if we're going to be in 3 clouds, we probably need some type of Kubernetes that we can have a control plane in all 3 clouds. And that way, if a single cloud fails, we don't have a problem. For example, we're going to talk about the Google Kubernetes engine. It is a wonderful, excellent Kubernetes engine. It's terrific. It's managed Kubernetes. And Kubernetes is great. And Google, kind of invented Kubernetes. So this is a strength of theirs, right? Here's the challenge. If our control plane is only in Google and Google were to have a catastrophic outage, we have no control plane running, say, our data center in the Azure cloud or the AWS cloud. So we may want to look towards something like an IBM OpenShift, which is a managed environment that we could put servers across clouds or that kind of environment, or a Kubernetes environment across clouds. But if we're not multi-cloud and we don't plan on being anywhere in the near future, we can use the Google Kubernetes engine. And that is going to be a fully managed Kubernetes service that will automate the deployment, scaling, and management of Kubernetes applications. So instead of managing your own Kubernetes cluster, the hard work is done for you by the cloud provider. So we can use this with self-managed clusters, where users are managing the underlying nodes, or in an autopilot node where basically Google Kubernetes engine is managing the infrastructure. Because it's made by Google, it's going to integrate beautifully in the Google Cloud with things like cloud monitoring, cloud logging, and even cloud storage for observability and storage. So kind of keep that in the back of your mind. Whenever we go with a cloud provider's thing, they integrate so smoothly with that same cloud provider. Now, there's basically 2 modes that we can use with regards to the Google Kubernetes engine. There is the standard mode where the users manage their Kubernetes modes, and that gives them full control over configuration and scaling. And then, of course, there's this autopilot mode where Google Kubernetes engine takes over the infrastructure management. And that enables users to focus more on their containers and their containerized applications on their code and less on the Kubernetes infrastructure and the infrastructure in general. So for organizations that don't have critical, significant performance needs and need great control, then autopilot could be convenient if this is an appropriate solution for you in your environment. So why might we use containers? Well, containers are elegant for a lot of reasons. We talked about the virtual machine versus the container environment before. And we talked about how each virtual machine, and I'll go back to that if you want, each virtual machine has to have its own operating system. And when we want to create an operating system, it may take, depending upon the operating system, a couple of gigs of DRAM to run the operating system. It could also take a lot of CPU cycles, maybe 10 or 15% of the CPU just to run the operating system. And that means that's a lot of overhead for virtualization. Where if we go to the containerized environment, if we really think about it, all we need to do is run the app and dependencies, and we're only using a single operating system. So these are lightweight. Plus, we've got a container that's got the app and dependencies. It's so easy to move it from one server to another, to move it off the Google Cloud and put it on the Azure Cloud, and off the Azure Cloud and onto the AWS Cloud, and off the AWS Cloud and back into the data center. So containers are great, and they're lightweight, and they're very, so they're being so efficient because they're using the host kernel of the operating system. So that's where the overhead is going. These things can be scaled out easily. Add as many Kubernetes as you want. And this is typically great, and it's typically one of the things we use Kubernetes for. Add capacity on demand. So, and containers are usually easy to deploy. We're not dealing with operating systems. We're not dealing with as much stuff. So easier to deploy, faster deployment. It's that lightweight versus heavyweight environment that we're talking about. And if you look at it, I always looked at, there's a couple ways you can look at these situations. We can all look at them differently, but I typically use virtual machines for when we need the maximum performance. In fact, Lonzo from my team drew the chart. I think it'll help. So a virtual machine is heavyweight. And what we're actually dealing with, it's whatever performance is based upon the CPU. It can be the highest performance thing in the world if we've got a lot of CPU cores. We're low if we've got limited cores. Each virtual machine on the server has its own operating system. The virtualization is done in hardware, so it's going to be very, very fast. But the startup time of a virtual machine could be a minute or 2 minutes. And each virtual machine is going to take memory. And it's going to be the most secure because it's really isolated by the hypervisor. When you look at a container, you have to think how light they are and how portable they are. So a lot of containers can give us good performance, but containers themselves typically don't have a lot of performance unless we add a lot of them. All the containers are sharing the same operating system, which means it's potentially less secure than the virtual machine where the hypervisor is providing it. Containers start up fast. Less than a second, typically, potentially even in milliseconds, and they require less memory space. So it's all about what we're using as it pertains to any architectural option. If we look at the two by comparison and side by side, you can still see that containers offer much greater efficiency, but they don't typically offer the level of security that you would get in a virtual machine or the control that you might have of the virtual machine. Now let's talk about where you could host those virtual machines. Those containers. So, Google has something called Cloud Run. And Cloud Run is something will basically auto scale your containers based upon incoming HTTP type requests. So what Cloud Run will do is it will abstract away the underlying infrastructure manager, giving you a serverless experience. So instead of thinking about provisioning servers and managing servers, the developers just focus on code. But again, you lose control when you focus on code. And when you need maximum performance, you often need maximum control. So it becomes what you're choosing, agility and convenience versus control. Your performance needs will dictate this. Cloud Run for Anthos allows users to run containers on a Kubernetes cluster. So it gives you some additional control of what you're actually dealing with. Cloud Run is typically very good for applications with spiky traffic patterns, such as a web API, where you kind of need that automatic scaling in and scaling out. Now, where do you store these containers and where do you store the container images? Well, you're going to need some form of container registry, a secure environment to secure these servers. And like everybody else, Google actually has a storage environment. So that's called the Google Cloud Registry. They also have Artifact Registry, which is also going to be managed by the Google Cloud for storing and managing container images. So artifact and an architectural artifact is typically a piece of documentation, but there may be other types of artifacts that you deal with, like a piece of code could be considered an artifact to a software developer as well. So there's a concept of an artifact registry. And this is going to be a more advanced version of the Google Container Registry for storing container images. While both of these are going to give you access control and good availability for your container images, Artifact Registry is a place to store your container images and it's going to integrate much easier into other Google services like Cloud Build for CI/CD pipelines and the Google IAM for fine-grained access control. So it's going to be a comprehensive and secure container management ecosystem because you're going to be dealing with this. It'll help work your CI/CD pipelines. You'll be able to store it in a secure environment. So that is the Google Artifact Registry, and it's going to integrate nicely with other Kubernetes, other environments. Continue our discussion on containers. Let's talk a little bit more about container orchestration and Kubernetes. So what is Kubernetes? Kubernetes is an open source container orchestration platform. It's used for automated deployment, scaling, and managing containerized applications. It's going to help solve the problem of running containers in a distributed environment. And it provides features like automated rollouts, service discovery, load balancing, and storage orchestration. So the point is, it's the control plane. And as I mentioned, you can build your own Kubernetes cluster, and Google, of course, has their own Google Kubernetes engine. So Google Kubernetes engine is going to handle everything from cluster creation to customer upgrades, scaling. So it all goes back to that focus on writing your code, not worrying about infrastructure philosophy. And sometimes that's a great philosophy, and sometimes it's not. So if we talk about the managed Kubernetes solution provided by Google Kubernetes engine, it's going to be there to manage and scale your containers. And it is open source. It is the standard Kubernetes. But I also did talk about what happens if the Google Cloud goes down. Now, if we think about Kubernetes, Google's really has a lot of experience here, probably more experience than anyone else, given the environment of Google, given the developer culture of Google, and it basically being a development company. They needed an environment where they could create a large number of containers and large number of microservices based applications because it worked within their culture. Thousands and thousands of developers all creating reusable code patterns that could then be reused in their environments. Kubernetes made total sense, and Microsoft and microservices in many cases architecturally made sense for Google. Sometimes it makes sense for other companies as well, and sometimes it doesn't. But in Google's case, they are experts with Kubernetes. So if you're dealing with a cloud provider's managed Kubernetes background, understand Google has a tremendous amount of experience. If you're there, they have had a lot of experience with their Borg. And Google has some pretty large-scale data centers. So if we think of this Google Kubernetes engine, it is an enterprise-grade Kubernetes environment. And it took the basic open source Kubernetes and it turned it into a very nice managed solution. And it's kind of a hybrid between giving you the control for an infrastructure as a service environment, and yet it's a platform as a service kind of mixed into one when I think about Google Kubernetes engine, because it gives you the control that you might need of your Kubernetes infrastructure, but you're not really managing that Kubernetes infrastructure and the servers, then typically speaking, in much the same way you would if you did it yourself. So it's going to be smooth and simple and fast and elegant on the Google Cloud. There's no vendor lock-in with this. And let's be fair, we could use the Google Kubernetes engine on Google right now, and years later determine we need something different, switch to IBM OpenShift, Red Hat OpenShift, and all of our containerized environment is good. We just use a different control plane. So this is good. No vendor lock-in. And again, it could manage our data center too, because it is great. Kubernetes is just what would happen if we only put it in Google and Google were to fail and the other cloud providers were still up. So that's the only time you might think of using something different multi-cloud for those reasons. Now let's talk about the shared responsibility model with regards to Google Compute, the Google Kubernetes engine. So remember, in cloud computing, you're responsible for your stuff and they're responsible for their stuff. And that changes based upon what the stuff is. If it's a software as a service application, they're responsible for everything. And pretty much the only control you have is how you use the application and your usernames, passwords, and your IAM stuff for the most part, your permissions. Whereas in certain responsibilities like infrastructure as a service, you have to manage your virtual machines, you have to manage your storage, you have to manage your operating systems, you have to manage much more of your network. So depending upon what's needed, depends upon what you're at. So let's talk about the shared responsibility model with Google Kubernetes. Google manages the infrastructure here. So you don't have to think about managing the virtual machines. Google manages the operating system on Google Kubernetes engine nodes. So basically speaking, that's taken care of for you. So these things are upgraded, patched, and secured for you, so you don't have to think about it. Google updates and maintains the Google Kubernetes distribution, so it's taken care of for you. Google is responsible for the control plane, the master VMs, the API server, etc.d, for example, the databases, and it's going to integrate beautifully with other Google services. Again, this is a nice service. Just think about it in multi-cloud, but it is a great service. Now, what is the customer going to be responsible in this situation? Node management. So the customer will be responsible for the nodes running the Kubernetes workloads, including any additional software or configuration of these nodes themselves. The workload security. The customers will manage and secure their applications, containers, their IAM configurations, and network settings. Keeping the nodes updated, whether you're using custom images or custom configurations, customers must keep their nodes up to date. And the applications and the environment, the customers are still responsible for the deployment and management of their workloads in the Google Kubernetes environment cluster, the GKE environment. So if we think of the GKE cluster architecture, it's going to be the foundational unit of Google Kubernetes engine. It's the environment where all Kubernetes objects and all workloads are going to be deployed. The Kubernetes cluster, just like standard Kubernetes. Now we're going to have the cluster master. Now this is going to be the core component of the cluster. It's going to be responsible for running all the control plane processes, the primary node or the cloud master. But we'll also have other nodes there in case the primary node were to fail. And we'll always need an odd number of nodes, generally speaking, for this type of control plane. So we'll need a minimum of 3, and that way we can have an election to determine who's going to be the leader, and we need a tiebreaker. So keep that in the back of your mind. Typically speaking, for any kind of control plane of any cloud, you typically need an odd number, 3, 5, 7, 9, that kind of thing. So let's talk about the cloud master. Now that's going to be the core component responsible for the master node. So let's talk about the API server and what it's going to do, which is going to be part of the master node. And that's going to manage the API calls and interactions with the cluster. That's going to be the central hub for communication between the cluster nodes, the controllers, and the system components. So think the master node is responsible for a lot. The API server that manages all the API calls and interactions in the cluster and all the communication. Now we have the scheduler. And the scheduler assigns pods to nodes based upon requirements availability. And the resource controllers manage the state of the cluster, ensuring that the desired state matches what it's supposed to be. So with Google Kubernetes Engine, we've got the K8's API server, and that's going to be the main endpoint for facilitating interactions via things like HTTP or remote procedure calls, that kind of thing, those type of API calls. Now, of course, in any kind of Kubernetes, we're going to have this kubectl, which will be a command line tool that is used to send these API requests. And that's how users can manage these cluster resources, nodes, and system components. A node is going to be where the work is done. The node is the worker node, the data plane. And here is where the containerized applications and workloads are going to be executed. The nodes are like typically running in a compute engine instance, for example. So if you think about it, you've got the control plane. And the control plane is the API server, for the most part, the scheduler and the resource controllers. And that's controlling everything that you're typically dealing with. The node is where the work is actually done, typically a virtual machine. And the pod is going to ultimately be the smallest deployment of in Kubernetes. And that's going to be 1 or 2 containers that you might have running on a node. So I want you to think about it. You've got the node where the work is being done. And then on that, you'll have a pod. And the pod is basically running a container or 2. So I kind of hope that makes sense to you. Now, Google Kubernetes Engine is going to natively interact with everything beautifully on the Google Cloud. Persistent disks, so you could store your container information in block storage, persistent disks, load balancers to distribute your crowd traffic across containers, and cloud monitoring, obviously, to track the health and performance of your cluster and what's going on. So when it comes to configuration and customization and scalability, Google Kubernetes Engine will allow businesses to build highly customizable, scalable, and resilient applications. And what it's doing is it's abstracting, or it's taking away or hiding much of the work for you. It provides cluster level and pod level configurations. So we can tune things on the cluster level, the top of it, the control plane, or we can determine the state and of what we need to do or change things on the virtual machines. For example, with regards to the individual pods, we could create for greater size virtual machines where these pods run. Remember, when it comes to storing information and cloud computing, where does it go? From a virtual machine, it typically goes to block storage. When it comes from a container, it typically goes to block storage. So we can attach persistent disks or block storage to the cluster nodes. And specific pods can be configured to share these kind of storage volumes. So that way we can have data persistence across restarts of our containers. Same reason we have block storage for data persistence across a reboot of a virtual machine. These two things should sound a lot alike because in many cases they're going to be. Now, when it comes to Google Kubernetes Engine, we have something called stateful sets. And they're used for deploying stateful applications that require persistent storage. So stateful set provides identities and stable host names that you're going to be using. So stateful sets are going to be useful for applications that require consistent storage. We have the concept of the horizontal pod autoscaler, and that will automatically adjust the number of pods in response to changing demand. So this way, if we need more, we can add more. Now, we also have the vertical pod autoscaler. So let's say our things are set to a limited number of resources, and we need more. The pods can be coming out using more resources as well. So it adjusts the CPU and memory resources, which is incredibly great and convenient. So we can dynamically scale the containers up vertically as well as horizontally. So a lot of power here. Let's talk about how we could upgrade the nodes, like upgrade these environments where these containers are at and where the systems are actually running. Well, we can do what's called rolling node update. And we could do rolling node updates in Google Kubernetes environment where you can control the disruption level your workloads are using. And there's these commands like max surge and max unavailable. So the point is, how are you going to update them? You're going to do a rolling update would be one opportunity. You can also do what's called the max surge. And that's going to determine how many additional nodes you can add during an upgrade. So why might you do this? Let's say you've got 10 nodes that are running right now, and you're upgrading and the performance goes away. With max surge, you can determine how many more you want to do during the upgrade to make sure your performance is okay. So think about that. We can also do that with a command called max unavailable or a configuration, and that's going to set the maximum number of nodes that can be unavailable during an update. So if we think about it, let's say if we need 10 at all times and we're updating a certain one, we need to make sure how many can be unavailable at a certain time. And if not, we're going to make sure a certain number will be. So max surge is how many do you want to add during the upgrade to keep the performance good. And max unavailable is how many can you tolerate not being available at a time. And then we can configure various surges, and different surge configurations will be a combination of max surge and max unavailable. So it'll help you balance the speed of your upgrades and the performance level that you'll have when you do these upgrades. Now let's talk about upgrading nodes a little more. We have to stay reliable at the time, right? So some businesses have 99.999% availability, meaning they can tolerate 5 minutes and 15 seconds of downtime per year and no more. So how do we update these? How important it is to be reliable of the system? So typically speaking, before we're going to make any change, obviously we need to look at it from a change management perspective and think of the impact of the business. But we can also think of how much performance do we need to add during the upgrades so we can tune things and nobody knows about it. So we need to think about when we upgrade, what performance do we need and how do we right size that? And that's where we have the ability to add with max surge, how many additional things do we want open, or max unavailable, how many things can we tolerate being down? And so that's going to give us a lot. Let's talk about auto upgrades. Most organizations don't like auto upgrades because it's scary, it's terrifying, you don't know what goes on. But using them in conjunction with an optimized surge configuration can make it a lot easier to patch because we can make sure systems are getting patched, taken offline, and new ones are being launched at the same time to keep it there. Now let's talk about cloud functions. So we talked about containers and what they look like. We talked about virtual machines and what they look like. So let's talk about a function. And a function is a serverless function, but it doesn't mean it's serverless. Typically what a function as a service is, so let's say we have our actual servers here, and they're sitting here. These are just a whole bunch of servers. And the way these functions are, you pretty much upload your code and you go. So the function is uploaded, this function as a service. And what will happen is this function as a service is going to need compute capacity to run. So we'll have this cloud provider's control plane. So let's call this the cloud control plane. And what happens, that enables you to run a function as a service. So you and thousands of other customers also have functions as a service that they want to be running on the cloud. And there's nothing serverless about it. It's called serverless because you don't have to think about it. So here's what happens. Something happens and your function runs. So your function runs. The control plane determines where it should run. It runs on one of these servers with extra capacity and the function is done. Now then the function is gone. Now the next function hits the control plane. It gets scheduled on one of the servers. It runs and it's then gone. The next function hits the soul plane. It hits the server, it runs, and then it's gone. The next function hits the server plane. It runs on a server and then it's gone. So what you can see, there's nothing serverless about this. Now here's the key. All you had to do was upload your code and it goes, and it runs on one of these servers. So what didn't you need to think about? You didn't need to think about CPU cores, DRAM, virtual machine sizing, patching your operating system, endpoint protection on your operating system, because the cloud provider did all that for you. Now, a function as a service could be very cheap, or it could be prohibitively expensive. And I want you to understand when it's going to be cheap and when it will be prohibitively expensive. I'd like you to think of taking an Uber every single day. So you have a choice of renting a car or buying a car or taking an Uber. And Uber is a good service. So let's say you live where I live in Florida. There's not a single thing that's not 10 miles away. And half of the things that I do require me to drive for 45 minutes or more. So if I go to the gym once in the day, which if I were to go to like a strength and conditioning facility near my house, I have one in my house, but let's say I went to the gym and let's say I took my wife out to dinner. Now, if I did that every day of the week, that would be 2 car rides every day of the week. If I used Uber, I might pay $20 for the first 2 car rides and another $20 for the second 2 car rides, which would be $40 a day. Now, if I did that for 30 days in a row, that would be $1,200 a month. Now, is that cheaper? Now there I outsourced all my driving. Now, by comparison, what if I could buy a car that was $400 a month? And that car needed $200 a month gas and $200 a month of insurance. So now to own the car, I'm paying $800 a month. And I can take that car anywhere I want. I can go to my 1-hour drives and not think about the cost of it. So in my case, it would not make sense to use an Uber to go places. It would be cheaper to buy a car. But what if I lived in the city? And what if I could walk everywhere I went? and only twice a week I needed to travel. Well, maybe then using the Uber would be so much cheaper than owning a car. Now let's bring that back to functions as a service. If there are things we don't use a lot or we use sporadically, these are one of the most cost-efficient opportunities out there. If by comparison we use it all the time, imagine I needed to take 5-6 rides a day. One was a 1-hour ride to Palm Beach Gardens, which is an hour in both directions, the gym, and I took my wife out. Now, in that case, my Uber bills could be thousands of dollars a month versus, maybe $800 of the car payment. So we have to think of workload. Same thing, if we're going to keep going with these functions that are going all day, every day, it's going to cost a fortune. But if it's sporadic or if it's event-driven or something like that, it could be one of the greatest tools we have. So understand that a serverless function is not serverless at all. We upload the code and it runs on a server. Where these do well is event-driven architecture. So let me tell you what event-driven is. If this happens, kick something off. So one of the problems we have as people in cloud computing is security of data storage, specifically object storage. Because in the data center, if you set the wrong file permissions, nobody outside the data center could see it in the first place. But in the cloud, your object storage is already connected to the internet. You potentially set the wrong permissions and provide the wrong link, and people on the internet can access your things. So we might use an event-driven architecture for every time somebody puts an object in an object storage bucket. If it sets it to public, we could have a serverless function remediate that and fix the permissions or fix the settings. So keep in the back of your mind, event-driven is when one thing happens, something else. And when we have these architectures that happen in response to something and they don't happen all the time, we often get much cheaper pricing with this kind of serverless function. Why? The cloud provider, realistically speaking, is an environment where they can just add capacity at any one time. There's typically not a lot of performance guarantees that are associated with these functions. It enables the cloud provider to build a lot of capacity and just run these workloads. So typically very good profitable service if you're looking at the ability to basically aggregate everything and not really anybody needs to know where it's at. And they can be very cost effective if your code doesn't run. Because there's two ways we could do an event-driven architecture. One is we could have a server running at all times to notice if something happens and react. And the other, we could have an event-driven architecture where if something happens, this thing gets kicked off and we only pay for it when we use it and not all the time. So I hope that makes sense. Now, Google Cloud Functions are open source format. So they will run, if you write the code in your data center, they should run on on another cloud provider's if the way you're writing the code is standard code that can run on a cloud provider's environment. Typically speaking, think of a Java or a Python or like a Python, something could run everywhere. And these are used for ETL jobs to kick something off often, or maybe to trigger something and a remediation of something. Maybe you get an alert of something and you want to do something about it, tell somebody about it, send a message. Lots of cool reasons to use these. So Cloud Functions are going to integrate beautifully with anything Google Cloud because Google Cloud Functions are made by Google. The platform's owned by Google, so it's very easy to integrate with anything. So it'll integrate well with any kind of HTTP request, typically cloud storage, cloud pub sub, cloud firestore, and even Firebase. And Cloud Functions will enable automatic forwarding of log entries from cloud logging to a publisher subscriber topic, which could then even trigger a cloud function. So you could have a CPU hit something, you could generate a cloud function, if you will, and notify somebody. So think about these kinds of things. Now, security here is going to be shared because the code's going to be executed on the Google Cloud. And the code execution is going to be under the cloud provider's responsibility because they're going to be managing these servers. It does reduce the operational burden of a lot on the end users. And for the most part with these things, Your creativity is the limit with how much you can do for these things. You can have an incident or something and react to it, or an unplanned event and create a trigger. So there's a lot of really incredible things we can deal with these kind of functions on cloud computing environments. Now, it is serverless, which means you don't know where it's running, which means you have no control, but there's also nothing for you to manage. These are typically stateless functions. So each thing that has to happen is typically stateless. So that means we may need multiple things and something to coordinate them. But these are typically stateless containers that don't retain state in between requests. And it's all about Cloud Run is all about abstracting the complexities away from managing different types of containers, different types of virtual machines. All in all, upload your code and it's just running. It uses the open source Knative framework, which is an open source serverless type environment, which is great. And that means we can use it fairly easily with other environments. It's relatively easy to use, straightforward approach. And, you may see it on the exam. You may not see too much of a function, but this kind of environment you'll hear a lot of. Let's talk about API management and some challenges in API management as it pertains to what we're describing here, containers and other things. So creating, managing, and publishing APIs can be relatively complex, especially when we need to maintain consistency on APIs. And application programming interfaces are how one system could talk to another if you're new to this world. And all in all, there needs to be a management platform to manage these APIs. Modern APIs need some way to be able to make sure they're consistent, they're secured, and they're deployed consistently across the enterprise in a policy-based manner. So keep that in the back of your mind. There are platforms like Apogee that have a fully developed suite of tools to handle entire life cycles of APIs. So let's talk about some comparative solutions. While API provides robust, full-featured platforms, there are other solutions like cloud endpoints that may lack some of the features needed to manage APIs. So we need to think about consistency. We need to think about governance. So we need some kind of an API management platform that will help enforce consistency across all API endpoints, because we need governance of our API endpoints or anyways where people are attaching to any of our systems. So we can think about that. So let's talk a little bit about Apogee. Apogee is a full end-to-end API management platform complying with open API standards. It's going to manage the entire API lifecycle across any cloud, multi-cloud, and hybrid cloud environments, which is great because that's the reality of our world. Apogee has been recognized as the leader in API management since about 2020, or at least that's when they first were from Forrester in the Q3. And one of the things we need to think about is it gives us API management. So one of the features is an API proxy. And Apogee can act as an API proxy, presenting backend services as a single managed API to a client. And it'll support modern client-facing REST APIs, even if the backend doesn't support HTTP, microservices, or modernized technologies. So it's going to function as a transition layer, as a proxy. And we talked about other proxies where in a proxy you connect to something and it does something for you. So we can think of Apogee providing that API proxy services, being that proxy to whatever your backend thing is that you're dealing with. Apogee gives us a degree of control and security over our APIs. We can look at things like transaction rate, access controls, and control it. Maybe we don't want to send too many messages to an API because we want to prevent a DDoS attack, for example. And Apogee helps businesses expose their APIs to clients without having to modernize the backend system. So in this case, what we're describing here is modernization without reinvention, because it enables businesses to modernize what they're doing, to update their publicly facing API layer without having to revamp. So Apogee does a great job. You should always keep track and see what other companies are involved, but Apogee does a good job here. Let's talk about cloud endpoints and what they really are. Cloud endpoints are really an API management platform designed to secure, manage, and monitor APIs. So it's going to simplify API management by reducing the need to handle APIs manually in Google Cloud. There'll be a developer portal where cloud endpoints are going to allow the creation of API documentation that will be accessible via the developer portal, and it's going to make it easier for developers to be able to access and interact with the APIs. When it talks about cloud endpoints, let's talk about secure communication protocols. So it supports 3 communication protocols: Open API, gRPC, and Cloud Endpoint Frameworks for App Engine standard environments. Now, in here, the reason people are using these environments is to enable the teams to focus on developing their API, as opposed their interfaces into their system, as opposed to creating custom frameworks to manage these things. It's about standardization and simplicity. So let's talk about a little tiny bit about API security, just a touch, not enough that you would cover, for example, in a security program. But let's think about some API security considerations. APIs, your programming interfaces, expose application logic or business logic and potentially sensitive data by the way they're designed, because they're going to be enabling one system to connect to another. So because of this, APIs are good targets for attackers. So we want to think about tools like Apogee and Cloud Endpoints that can prevent flaws by default or offer configuration management. And of course, we're going to need to think about how do we protect these APIs with, say, IAM, packet filtering, firewalling type options, and many other things as well. Now, we need to classify our APIs. So when we manage them, there's going to be different API security that's going to need for things that are publicly facing, meaning facing the internet, that are being internal for internal uses versus partner facing or third-party providers. And typically we will need lots of ways to do this. We typically want to put an API in a demilitarized zone, a special security segment that would be segmented if it's going to go to somebody externally. So we have to think about API security the entire time. One of the things we may do with APIs and network security is we don't want stuff coming at us too fast. What if somebody tried to create a distributed denial of service attack and overwhelm something? So we might rate limit it. So for example, in network security, if we've got traffic that doesn't feel like normal traffic, we might limit it to 10% of the link or just drop it periodically. Now we still want to do the same thing. We want to rate limit the API things. What if hackers tried to DDoS it by sending 1 million requests? Well, if we rate limit it to something that we know our systems can handle, those requests won't even hit the API to actually damage the API in the first place. We have to be very careful on our APIs that we don't expose any unnecessary data. So we need to filter any unnecessary data long before displaying an API to an end user or a third party. When it comes to configuration and monitoring, we need to use consistent configurations and constantly monitor our APIs for any kind of security misconfiguration. We should think about things like input validation. We need to validate the inputs that are going to go into the API to make sure that we don't allow for things like an SQL injection, for example, or the input of malicious code. We probably want to use what's called IP whitelisting. So whatever you're going to do is you're going to determine which IP addresses need access to it, and you'll whitelist those. And at least those will be the ones that get through. We typically may want to use load balancing to place APIs behind like a application load balancer, in certain cases to load balance between them for scalability purposes. And we need to be able to authenticate anyone that's interacting to the API. So we need to start thinking heavily about our IAM mechanisms, specifically the mechanisms of authenticating one system to another system. Okay, we are back. And as it turned out, Chris did a poll in the audience and saw if anybody wanted to play more, learn more about virtual machines and containers. So the answer was an overwhelming yes. So I decided I was going to start to put together a little demo, and then I was going to walk you through a whiteboard and a demo at the absolute same time. So let me walk you through the virtual machine architecture, and then we're going to go build one. And then we're going to talk about the interplay of virtual machines and containers. If you want, we can talk about secure operating systems
versus standard operating systems and the way they're actually containerized. And we'll look at all how these play together. So let's go back. I want to just do a quick whiteboard as a reminder of what we're dealing with. And then I want to take you to a real server, and I'm going to take you to the real hypervisor. I'm going to walk you through. Then I'm going to show you how in the data center virtualization has worked for the last, say, 26 years. And when you understand that, you'll know exactly what's going on there. And basically, if you're taking a virtual machine from the data center to the cloud and you don't understand what the virtual machine is in the data center, you're not going to understand it in the cloud. So let's start with that. So let me begin. I'm going to produce a little whiteboard slide over here, and then we're going to go to my hypervisor. In this whiteboard slide, remember I said we start with a physical server in all of these virtual machine environments. Now, this is the server. Now, if we wanted to, and we needed the greatest performance, and bear with me, I've got to adjust my magnification here for you to see everything. But if we wanted to, we could easily install Linux directly on this server or Windows directly on this server and have a giant high-performance application. We could. And I've worked on systems where latency is everything, and where we need the maximum performance out of a server, we don't run it in a virtualized environment. We run it directly on the server itself. Now, the majority of the applications out there don't need that level of performance of a single server, so it's not that common. But if you're going to work in banking, for example, or you're going to work in an environment where nanoseconds equal many, many millions of dollars, then you're going to run directly on the server. But let's say this server has 384 physical cores on it and 10 terabytes of DRAM. Chances are that's going to be enough for 50 virtual machines or more. So remember, with all of these environments, we're going to have a hypervisor, and then I'm going to bring you to a real hypervisor in a minute. We're going to walk through that hypervisor itself. It's going to be a hypervisor. And then on that hypervisor, we can create many virtual machines. Virtual machine 1, virtual machine 2, for example. And I want you to think about how cool this actually is in this virtual machine. And I'll show you on the hypervisor. This virtual machine is ultimately a single file, something that could be moved from one server to another physical server at a moment's notice. Cloud provider wants to take your server down, the server that you're sitting on right now, because they need to take it offline for maintenance. They can just move your virtual machines to another server and you stay up. We do the same thing in the data center since this existed, since this was created. Now, this hypervisor was created by VMware in 1999. It is the basis of all hypervisors. Linux offers a few hypervisors, KVM, QEMU, and all cloud providers are using some form of a Linux hypervisor, but it all came from VMware in 1999. It's the same technology. Now, let's extrapolate into one of these virtual machines. We might now create a virtual machine. Now, if we look at this virtual machine itself, what is a virtual machine going to need? It's going to require an operating system, as nothing will function. And then maybe we want to put containers on this virtual machine, and we're going to need to keep the containers separate from each other. Well, then we're going to need a container runtime module. So that we can, and I'll show you that in a second. Then we'll go to the real hypervisor. Now, this container runtime is what's going to be needed to enable containers to run on this system. Now, often you might see the interplay between Kubernetes and Docker. And what's going on is Docker is the runtime module for the containers that say sitting on this Linux server. And meanwhile, you're using Kubernetes as the control plane. So you've got this Kubernetes control plane. And then you have to have at least 3 nodes, because these things have to run an election process to determine who's the lead. And what'll happen is this control plane will then control the containers, whether to scale in, whether to scale out, whether to add containers, whether to remove containers. And meanwhile, these containers are running on side of this server with the container runtime module in an operating system that's sitting on side of typically a virtual machine. So let's go to my actual, and we can go back to this, but let's go back to my environment. I'm going to go to use this. This is great. This is a virtual machine I built a little earlier. I'm going to restart it, and then we're going to build one together. So this is a physical server, a regular server that you would see in a data center running pretty much the industry standard hypervisor, which is VMware ESXi in some way, shape, or form, typically included with a vSphere package where an enterprise can manage the systems, their global environment. But this is pretty normal. Now, if you look in this environment, which is pretty normal, there's a couple things I want you to see. If you look in this upper right-hand corner, and it's not the easiest thing to see at the current size. Let me see if I can make my browser look a little bigger to make it easier to see, and I'll zoom in and zoom out as we do this. But if you look carefully at this server, you can look at the CPU. You can see the CPU has a cumulative of 53.6 gigahertz left of capacity, compute capacity. It's got 109 gigs of DRAM left available, and it's got about 700 gigs of storage space. Now you can see that some of the storage space is used. This is for various virtual machines. You can see that some of this memory is used, and that's probably because virtual machines are running. Now, if you look a little carefully, you can see this is it's a Dell workstation, typically with server processors. These are Intel E5 2670 V3s. These are fantastic ones to use. And if you're curious about building a lab, or a lot of businesses, these are considered, even though the processor's end of life, these are typically considered standard compute on a normal cloud provider. These cost about $1,100 a month to rent these servers on a cloud provider, but you can buy them from Amazon for about $400 as refurbished gear. If you ever wanted a lab in your house, just keep that in the back of your mind. And also, it gives you the cost sometimes of comparison between running it on a cloud provider versus running it in your data center. Now, it's end-of-life gear, but just think about all these things. But you'll see as there's 24 CPU cores in here, physical cores, and you'll also see that there's 48 logical cores. Remember when I talked about hyper-threading the other day, and I talked about a processor being able to split its cores? You know what, just for the fun of it, let me go back to that real quick before we actually get in, and then we'll have some fun with this. But let me just go back to that and make sure. Oops, no, bear with me one second. So if you'll recall, when we went over system architecture, that the chip will have multiple cores on it. For example, if this was a 4-core chip, which really wouldn't belong in any server in today's world, but let's just pretend it was 4 total cores that we have going on here. In this particular environment, what can happen is if the load coming into the core doesn't utilize all of this one core, this physical core can virtualize itself into 2 logical cores. So in a physical world, we get physical cores. When we rent virtual machines and it says 8 cores, these are 8 logical cores, which is 4 physical cores. So keep that in the back of your mind. Now, when we go back to my hypervisor, and now you see that it now has 2 processors with 12 physical cores per processor, which is how you get 24 physical cores. That's how you get the 48 logical cores, which is why I said core performance is not the same in potentially a physical server as it would be a virtualized environment. Now, if we also look through this to get you a feel for what these things look for, here's going to be the process to create a virtual machine on a server. And I want you to see what it is, because remember I said CPU, when you size a virtual machine, it's about CPU cores, and it's about DRAM and or network performance. Well, this is typically the way it would be created. Now, it would typically be created something like this. I'm going to name the virtual machine. And since I'm a security person, I will do all the things when I name this virtual machine and create the virtual machine you wouldn't do, to hopefully make you understand the security rationale. First, I would not call the machine Cindy the cat, because everybody knows Mike loves cats. So I would never use the word cat. I would never use the word Cindy. I would never use my pet's name as a password, as a this, as an anything, but just think about that. But well, instead of calling it this, I was going to call it Cindy the cat, but let's call it Google Bootcamp 2. But I hope that makes sense about why you wouldn't want to do that, because it's too easy to do. Now, then we're going to tell it the kind of operating system we want. We're going to tell it Linux. And then we're going to pick an operating system version, and we're going to tell it Ubuntu. Now, what I'm going to do is walk you through the first part of the setup, and then I'm going to open up a virtual machine I just created so you could see it. And I did that in the last few minutes. So let me move this up because we're going to have to go back and forth and zoom in and zoom out so you can see it. The next thing that we need to do is we need to say, how much of the resources from the physical server are we going to put in this virtual machine? And we have an option. So let's say it's a Linux machine. Let's say we need 4 physical cores. Let's say the machine is a very small Linux machine. It needs 8 gigabytes of DRAM. Let's say the hard drive for this virtual machine is going to be 20 gigabytes. And then realistically speaking, we would have the ability to specify custom settings for a virtual video card, or we could put a physical GPU into this virtual machine for AI purposes if we wanted, or 8 virtual GPUs into this virtual machine if we wanted, if they were on the system. Now what we need to do is go to the next phase where we need to tell it where it's going to boot from. And I'll pick Ubuntu 22.04 desktop. Looks like a fun thing to install. If I click next on this, you'll be able to see the virtual machine, the cores, the DRAM that it's going to pull. And I want you to notice something. So right now, very carefully, look at the amount that we have. We have 53 gigahertz free. We've got 109 gigahertz free. So let's see what happens when we click next. Now at this point, let me kind of put this in a better spot. Let me show you. So we've now created the virtual machine, so it should be sitting under our virtual machines. And we're going to turn on this virtual machine, but I want you to go back and see this. Note we've now got 54.9 gigahertz capacity, probably because what we were doing before was taking CPU cycles to create that machine. Now let's take this virtual machine, Cindy the cat, or virtual machines. Let's turn on this Google 2 Bootcamp virtual machine, which we just made. And let's first do 2 things. Yes, hold on. We want to install it, but let's go back to the host real quick, just so you can see something. Notice some CPU resources were gone. Now you're going to notice as this virtual machine comes up, it's going to pull more resources from the main server. So we're going to boot this system. We'll install it. Continue. We're not going to do a very sophisticated install here. We're not going to download updates to make it very quick. We're going to do a very minimal installation here. So it doesn't take very long. So we'll erase and install. This is going to be pretty quick. Maybe we'll even work through it. It's going to tell you what the partition table of your drive is. And the key here is when you look at it, I want you to see that it's very similar in the look and feel to what you'd see in real life if you did it on your own notebook. It's exactly the same. It's using a virtual one. So we're going to use the username Cindy. Again, I don't want you to ever do something like this. Now, when it comes to cracking passwords, with 24 RTX 4090s, we can crack an 8-digit password in less than a minute or so. So if you think about that, you probably don't want to use a password. Maybe you want to use a passphrase, which is harder. Maybe you want to use 16 characters, or better yet, use something that's not a password. Because imagine how easy. If I use Cindy, how hard is it to go to social media and find Mike has a cat named Cindy? Or anything that you would know. So please, pick things that are obscure and wild and crazy. Well, I'm going to call it 1, 2, 3, 4, 5, 6, because we know that's not a good idea. 1, 2, 3, 4, 5, 6. And the reason it gave it a fair password is it wasn't smart enough to know how ridiculous of a commonly random password that was. There was a point where the most common password on the internet was Cisco. And I'm not joking, because it was part of a certification exam. So people just put it on the router. So just think about that. Now, give this about a minute, because I didn't ask it to actually update itself. And then you're going to see that it's going to look and feel just like the real thing. And then I'm going to boot up I'm going to show you there's another virtual machine while this thing is doing its thing. I also want you to see that there's other things running on the same thing. For example, here's another virtual machine. We can turn that on and you can see it. Now, this is another Ubuntu server that I had installed while we were on there as a demo in case this was going to take a long time to do. Now, while these two are running, you see now there's two. Now let's go to the host and move it out of the way. And look, wow, we only have 49.5 physical gigahertz free. Now we only have 101. Where do you think that's coming from? It's coming from all the resources of the second virtual machine. But look, I have two servers. The first one has 8 cores, and the other one that we're creating right now has 16 cores. So 8 and 16 is 24 cores, but it's not using 50% of my CPU capacity. Now, these two machines, I want to say it again, these two machines are scheduled to use 14 physical cores from the server. So if this server has basically 48, 14 divided by 48 is about 25%, but note it's only using 10% of the CPU, including to run the hypervisor. And why is that? That is because most virtual machines don't use full capacity at the same time. Now think about this. This virtual machine and this virtual machine are probably only using 8%, even though they could be using 25%. So understand that it is common practice in a service provider to sell possibly more of these virtual machines than they actually have physical capacity for. And it works on the statistical anomalies of not all these virtual machines are using the same capacity. Your internet service providers do it in the way they send their bandwidth, for example. And that's why, like, for example, when COVID happened and we all started working from home, people didn't expect the internet service to be that big and that bad. Okay, so it is actually trying to update it. We'll go back to this and we'll go back to our drawing and we'll come back to this in a minute. So bear with me. Now, if we look in a large-scale virtualization environment, and this is like any other cloud provider, what are they going to have? They're going to have tens of thousands of servers. Also, we'll pretend these are all servers. And when we have this, the cloud provider is going to have their control plane. And then when you create a virtual machine on the control plane, or you click for one to start up, that virtual machine, I desire to open this, hits the control plane, often via an API, and then that provisions the capabilities here. So many of you have interacted with the control plane, well, the part of the control plane. So if you log in and use the management console, the console that's Leo showing, that application of that console is going to feed into the control plane, and that's going to create that virtual machine on one of these servers. And that control plane is going to create your virtual data center in here. And your virtual data center, again, is just going to be your VPC. So that's your virtual data center. And this is created logically in the memory of the servers. And all this networking that's going on inside your VPC, that is virtualized networking called software-defined networking. Let's see if our virtual machine is finished doing its installation. Okay, it's almost done. It's going to reboot in a couple of seconds, and we should be fairly good here. And then we're going to turn on this virtual machine. And when you see this, now you know exactly what's going on under the hood in the cloud provider's data center. They're going to have an orchestration system, which you're going to interact with, and it's going to make the changes in there. Now, guess what? If you use infrastructure as code, it's going to interact with that same control plane, and it's still going to deploy that virtual environment. And it's all going to happen behind the scenes in an interaction with that control plane. Then that puts it on the servers, which you don't know where they are, with the exception of which data center they are for the most part. And that's one of the things that we're typically talking about. Well, it looks like that thing's going to take another minute. So let's have some fun with one more concept that we can talk about that you can typically do to increase performance, just a drop. And we'll typically talk about the placement of these servers. And you typically have various architectural choices. So let's say I had a system and the requirements of the system were as lowest latency as possible. Maybe this thing is a trading system and the trading system buys and sells options. And if it can buy it a nanosecond before the competition, so there's news that says this is going to go up. If you can buy it before the competitors, you can buy it cheaper. So if we were trying to create an AI-based trading system that's going to trade faster than the traders are, competitive advantage is latency. Now, in a high sensitivity latency environment, we might actually take all the servers, run them on bare metal, not versus a virtual machine, and you can do this in the cloud, and we may place them all on the same rack, all in the same switch. So what we have is incredibly low latency. This would be a rack. So we'd have a server, a server, a server, a server. This is typically the switch or a layer 3 switch. And we'd have all our stuff in the same rack. Now, obviously, this is going to give us the greatest performance in the world. Now, the architectural trade-off is if anything component here goes, you lost everything. So typically in these environments, we run 2 of them and we do a few other things to play with it. But just keep that in the back of your mind. Where we place this stuff will also have some degree of performance. You may hear that called placement groups or something like that in your cloud provider. Now, I think we're probably back. I think our virtual machine is most likely going to be finished here. Okay, it looks like it's doing the last possible seconds. We'll reboot it. We'll log into it, and you'll see what it is. Now, you can run these on your desktop if you've got a type 2 hypervisor, which is where you'd get like VMware Desktop or the VMware Player or the, I think there's one made by Oracle that's a freeware virtualization thing you can use on your system. If you've got Linux, you've got KVM or QEMU that you could potentially use as well. This happens to be what's used in most data centers, so I thought I would use it. And it looks like it's going to take an additional second or 2 for this thing to come up. Nothing's ever as fast as you want it to be when you're demoing it in real time. So we will come back to that. But that's really what we're talking about. Now, while it's doing that, let's talk about one set of architectural trade-offs. I did say I would talk about secure operating systems first. So let's talk about that fairly quickly. So what is a secure operating system? Well, or more secure operating systems. Many of them do this. So in a traditional operating system, here's your OS, and your applications all sit on top of the operating system. And they've been doing this forever. I'm sorry, this is an app. Since Pablo brought something up, and this is where certain operating systems actually work that are when you need security. So what you see in a normal environment is this. You've got your operating system and all your applications, and here's where things go wrong. If you can in some way escape one application and get into another application, one system could be hacked along the way. One app goes haywire and uses all the CPU memory and DRAM in the system, it can cause the system to crash. And many, many years ago, we used to see a lot more of that. Now, what some operating systems do is they literally virtualize everything from the scratch. So every application runs in a separate container. in a separate memory space. So now if each app is in its own container, like I've shown you here, theoretically, if the app inside one of these containers crashes, it shouldn't go over to the main operating system. That doesn't mean it can't, but it shouldn't. So some of the operating systems actually run all their applications separately in containers. And there are some servers that an operating system you can use to isolate memory space from one to another. But that is way beyond the scope of this. Let's go back and see if our virtual machine came up. And it did. So let's play with this. We'll bring our virtual machine back up. And I'll show you how it's going to look and feel just like any other Linux machine. We should be up in a couple of seconds. Okay, and you're going to see this is going to look a lot like any other Ubuntu Linux desktop that you might ever use in your life. But I do want you to think about one thing. Some companies use these remote desktops where you sit at your house and then you use a remote desktop. And why might they do that? Well, first, you can see this is going to perform relatively well. It's the first time. It might be a little slow. See if it's slower the next time. So these things are going to perform good enough. But if you VPN into their system and then you're using the system that's in the data center and it's not on your desktop, your data in this virtual machine never left my data center. And that way I could just back up my data center. And if you ever run into a problem, I could just create a new virtual machine for you as opposed to totally re-imaging your computing systems. So that's what you can see. This is exactly what you're getting in the cloud provider. It's just that you just select it and it starts, and they've got these things automatically deployed for you. So keep that in the back of your mind, and that's pretty much it. This is exactly the way virtualization works in every data center. You can see where the difference between the virtual machine is where the container would be. And then that brings us back to like one last concept to really think about. And that is those trade-offs between the two of them. So if we look at a virtual machine, we have the ability to get the most power. I could put all 384 physical cores in that virtual machine, or 768. I could put 4 terabytes of DRAM in that virtual machine. Now with a container, they're typically small compute power. With my virtual machine, they're pretty segregated from each other. And by pretty segregated, I mean this. Here's my let's go back to here. I'll get rid of some of this stuff. Here's my server. And here's my hypervisor. And let's get this out of the way. In this particular environment, I now have my virtual machines. Now, and most likely, these virtual machines are going to be in a different subnet too. So this virtual machine might be in a different subnet than this one, which is going to make it very hard for them to talk to each other without a router in between them. And you don't have routing in between these. So the only way that you could hack this would be to somehow escape out of the virtual machine that you were in, and somehow from that virtual machine be able to hit this hypervisor over here, and then hack into the hypervisor to be able to escape your virtual machine, and then to escape the virtual machine and enter another system that you'd have to hack into. That is really, really hard to do if your hypervisors are patched and up to date, and that's why cloud computing works. Now, if this is a container, and this is our VM with our OS, and then we've got a container runtime module to make this happen. And then we've got our containers. No, so you got a couple things that could enable this to go wrong. If you hack into the operating system of the system, you might be easier able to escape the operating system into one of these containers. If you hack into the container runtime module, you might be able to get into one of these containers. So theoretically, it would be easier to go from a container to a container than it would be from a virtual machine to a virtual machine. So you have a little more power with the virtual machine. Theoretically, you've got a little more security, but you've got a lot of overhead from all these operating systems. So I hope that little, we decided to do something that was fun in the short term, covering some virtual machines. I really hope that helped. If there are other questions, let me know. Otherwise, we've got some really fun labs from Leo on Compute to play with. Did everybody get enough of a live whiteboard session from what everybody was asking? So, and Claudia, so APIs could be load balanced in a lot of ways. They could be load balanced with an API gateway. They could be load balanced with a reverse proxy. The key is whenever you're load balancing for several reasons. You're load balancing to increase fault tolerance so you don't have a single point of failure. You're typically load balancing to increase performance. So you could do it either way. Now, if you load balance with a reverse proxy, you might be able to cache certain information as well versus a traditional load balancer. But you can balance APIs any way you want. Lots of ways to do it. The goal is, what do you need to do? Okay, Leo, good to see you back. So Leo, in case people, well, actually, if you're just joining us, as a reminder, we've got the first 5 days of the boot camp. You can go back. My team will drop a link to that in the chat box. If for some reason you just found us on day 6, welcome. In addition to going back to the first thing, we've got a free e-guide that's going to help you prepare for the Google Professional Cloud Architect exam. So sign up for it. My team will drop a link. Leo's now going to get into, I think, about 5 different labs. I know we talked about, for new viewers, Leo, what are your labs about?
Well, now we have demonstrations about how to create a custom virtual machine image.
Good.
And how to create instance templates to standardize how to create many virtual machines practically equal to each other. And we will use those instance templates to create managed instance groups. And once we have groups, we can use auto-scaling to cope with variable amount of requests. So those are the demonstrations we will see now.
Sounds fun. So give me a hashtag Google Professional Cloud Architect Leo's Labs. And in production, I'll ask that question, explain container runtime module. So let's say you wanted to run a container on a server. It has to run in something. You have to have something that separates my containers from your containers, and that's the container runtime module. So if you think about it, what is it that the containers actually need from the underlying operating system to run? They're leveraging the kernel of the underlying operating system. They're leveraging various packages of, say, the underlying operating system. But if we put container 1 and container 2 just on the same operating system, then you can leave container 1 and you can go to container 2. And if we just put it on the operating system without the container runtime module, we won't have anything to limit the CPU and the resources of it as well. So that's typically why we had that, which is why in that last diagram, let me go back to it. Whoops, wrong thing. When you work off of 4 monitors, you open and close windows, and you're terrible about reboots, finding the right window is always a bit of a challenge. So, okay, so if we go back to this graphic here real quick, which you were asking about, let me shrink that down so we can see it. So, and let's just put it on bare metal just to make life a little easier to understand this, because you could do this on a bare metal server. So if we have the server, and this is just the physical server itself, and then let's say we install Red Hat Enterprise Linux server, Windows server, Ubuntu server, I don't care. In order to have this container and say this container is Leo's container, and let's say Leo and I are in different companies, his containers and I shouldn't be talking to each other, right? So in this particular file, we've got Mike's containers, and because my cat, she thinks she's going to be a media celebrity and she's doing all kinds of crazy stuff. She has her own containers, and they are all three different businesses. It's that container runtime that almost to me, and this is like a more of a simile, if you will, than an actual technical thing. The same way we had a hypervisor on the server to chop it up into middle servers, this container runtime almost, it makes it like you're virtualizing the operating system. So this is separate from this, which is separate from this. And that's really what the container runtime module does. Meantime, the container control plane says, Leo needs 10 containers and one of his containers crashed, so he only has 9. Add one. Or Leo needed 10 containers, but the load on these containers is too much, so add 10 more containers. That's what your control plane's doing. And the runtime is enabling it to happen. I hope that helps, because that's a great question. Okay, well, I think we answered all the questions right now. If you have more questions, when we come back, we'll be happy to answer them. So, Chris, let's get back and let's start with the labs, Leo's lab. We're all looking forward to them.
Hello. In this lab, I will demonstrate how to create a custom image. You can create a custom image from an existing disk from a virtual machine. This means you can create a virtual machine from scratch, install all the softwares or applications needed, configure the virtual machine exactly the way you need it, and then, when ready, you can create sort of a clone of the disk of this virtual machine to create other virtual machines that are exactly the same as the first one or the original one. I will start here in the cloud.google.com page, and then I will use the search bar and enter create custom image. I will select the first link. We recommend you learn about the services you are going to use, so you can cover the contents of this page on your own. I will not cover all aspects of this page, but just do a simple demonstration on how to create a custom image. In the Before You Begin section, there is a link for the images document. I will right-click the image link and click to open in a new tab. I will switch to the OS images page. The content of this page is about the images that can be used to create virtual machines. So use operating system images to create boot disks for your virtual machine instances. You can use one of the following operating system image types. Public operating system images are provided and maintained by Google, open source communities, and third-party vendors. By default, all Google Cloud projects have access to these operating system images and can use them to create virtual machine instances. Custom operating system images are available only to your Google Cloud projects. You can create a custom operating system image from boot disk and other images. Then, use the custom operating system image to create virtual machine instances. Some operating system images are also capable of running containers on Compute Engine. I will scroll down the page I recommend you cover the content of the page to learn more about the operating system images. And here we have the operating system image costs. It says that premium operating system images, whether public or custom, incur licensing fees to run on compute engine. This is about operating systems that require paying a license for usage, such as Windows, Red Hat, and Ubuntu Pro, for instance. The last statement for this section is, for custom operating system images, you also incur an image storage charge while you keep your custom operating system image in your project. So please be aware about the costs of the services you use in the Google Cloud Platform. You can cover the content of this page on your own. I will close this tab and go back to the previous page. Scrolling down to the Create a Custom Image section, there is a Prepare your virtual machine for an image. You can create an image from a disk even while it is attached to a running virtual machine. However, your image is more reliable if you put the virtual machine in a state that is easier for the image to capture. This section describes how to prepare your boot disk for the image. So to minimize writing data to the persistent disk, one step you can take is to stop the virtual machine you are going to create the image from its disk. The second step is to disable the auto-delete option for the disk. I will go to the virtual machine instances page, and I will stop this virtual machine so I can create an image out of its boot disk. Now the virtual machine is stopped. I will click the name of the virtual machine to enter its details page, and then I will click the Edit button and scroll down to the boot disk delete rule. And here is, it's set to delete the disk when the virtual machine is deleted. I will change to keep disk and then click Save. The page refreshed. Now I will use the top left menu to go to the Compute Engine Images page. I will right click to open in a new tab and switch to that tab. And here we have a list, a long list of public images. I will click Create Image. I will enter name for my image. I will call it Custom Apache Web Server Image. The source is a disk, and I will now select the source disk. I need to go back to the VM instances page and check which one is the one I stopped, is 852. So I will go back there and select the 852 instance as the source disk for the custom image I'm going to create. The location, just for simplicity, I will select regional and accept the same region as my virtual machine exists. And I will just accept the other defaults and click Create. While the image is being created here, I will go back to the virtual machine details again and click Edit, and I will scroll down all the way to the bottom and just to observe if this virtual machine has any automation. And yes, this virtual machine was created with a startup script to install, to update the system packages and install Apache 2 and customize the index HTML file with a bare minimum web page here. Since this startup script was executed when the virtual machine started, the customization made by the startup script is already performed in the existing virtual machine. Therefore, the image of the disk of this virtual machine will be already updated and has Apache 2 installed on it. Let's go back to the images window, and the custom Apache web server image is ready. I can now go to the VM instances page, and I will now create an instance using that customized or that custom image. I will accept all or most the defaults. I will go to the operating system and storage, and I will click change. And instead of a public image, now I will select a custom image to create my virtual machine. I will open here the list of images, and this is not the one I want. I want the one that's called custom Apache web server image. I will select this one, accept the remaining defaults, click select. And just I did when I created those two virtual machines in previous labs, I will go to the networking tab and allow HTTP traffic, because I installed Apache web server and I want that web server to be reached from the internet. So I'm allowing HTTP traffic, and I will go to the advanced tab and make sure that the automation and startup script is empty. I will click create to create the virtual machine using that custom image. Now the virtual machine is ready. I will copy its external IP address, open a new tab and enter http:// and enter the external IP address of the virtual machine, and it shows hello world. This is the landing page of my Apache web server page. This is just the same customized web page as the virtual machines I created in previous labs. In this lab, I demonstrated how to create a custom image from an existing virtual machine, and then I demonstrated how to create a new virtual machine using a custom image. Thank you for watching. See you in the next lab.
Okay, we're back for a couple of quick seconds, just checking in on you, seeing if anybody needed anything out of the last lab. And if not, we'll go straight into the next lab. So let us know that you're awake. If you don't have any questions, maybe give us a hashtag Google Professional Cloud Architect or a hashtag Leo's demos are great. Whatever you want, just so I know that you're there. And we'll give it a couple more seconds, see if anything pops up. And if not, we'll go to the next one. And Leo, what's in the next lab again?
The next one is how to create instance templates.
All right, Chris, I didn't see any questions pop in, so let's roll with the content on how to create instance templates. And as a reminder, we have a
Hello. In this lab, I will demonstrate how to create instance templates. An instance template is a resource that you can use to create virtual machines individually or in managed instance groups. Instance templates define the machine type boot disk image or container image, labels, and other virtual machine properties. Instance templates are a convenient way to save a virtual machine's configuration so you can use it later to create virtual machines or groups of virtual machines. I will start by opening a new tab and visiting cloud.google.com. This is Google's entrance page. You can perform your login, you can access the console, and also you can access the documentation. I will click Docs to open Google's documentation, and from the left side menu, I will click Compute. Then I will click Virtual Machines, and after that I will click Compute Engine. This will open the Compute Engine documentation. We recommend you read the documentation of the services you are going to use to understand the services, the charges involved, everything. In this section, Documentation Resources, under the Guides, I have the option to choose a deployment strategy. I click this link to open the document, and again, you can cover the content of this document on your own. I will go straight to the point I want to highlight or to call your attention for the information. Here, under the review, the available deployment options, we see you can use standalone virtual machines depending on the use case you have. You can use unmanaged instance groups, and you can use managed instance groups. When using standalone virtual machines, you choose the machine type, image, disks, and other attributes individually for each virtual machine that you provision, and you manage the virtual machines as separate resources. When using an unmanaged instance group, you can provision standalone virtual machines and add them to an instance group. You can then use the unmanaged instance group as a backend to a load balancer. In this case, let's say you are running a web server. You can have several virtual machines running the application, the web server application, and use them in an unmanaged instance group, and you put in front of them a load balancer to distribute the incoming requests. When using a managed instance group, you would have identical virtual machines or similarly configured instances that you provision by using an instance template. So first, you create an instance template, and from the instance template, you create the virtual machines that will be part of the managed instance group. You can make a managed instance group stateful so that specific disks or metadata are preserved. For a stateless managed instance group, you can enable autoscaling and configure a scaling policy. If you are not familiar with stateful or stateless concepts, basically stateful is something that has a track record and keeps data, and a stateless is something that doesn't care about the data being processed. It does its job and then finish and start the next job. It doesn't keep track of anything. The important aspect here is that for a stateless managed instance group, you can enable autoscaling. Autoscaling is the ability or the functionality that allows the number of virtual machines inside a managed instance group to increase or decrease depending on the demand. When the demand increases, the number of virtual machines will increase inside the managed instance group, so the group is able to take care of the demand. When the demand decreases, the number of virtual machines can be reduced to avoid costs of virtual machines working with very low utilization. The last topic from the Manage Instance Group characteristics is, while creating a Manage Instance Group, you can choose to deploy the virtual machines within a single zone or distribute them across more than one zone in a region for high availability. I will keep scrolling down. You should read this page and understand the different concepts here. How to choose the strategy based on the requirements, the decision tree. And here from the What's Next session, I will click the link to learn more about instance templates. Again, read this page, cover the documentation to learn about the services. I will go straight to What's Next section and then click Create an Instance Template from scratch. This opens the Create Instance Templates page, and I will go down to the steps. The steps under the Create an Instance Template section. The steps I will execute now will create an instance template that can be used to create virtual machines identical to one I created manually using the console in a previous lab. The difference is that one can use the instance template to repeat the creation of virtual machines thousands of times, and they will always be equal, saving time and reducing the chance of errors. Here, on the step-by-step, the first step is to go to the Instance Templates page and then click Create Instance Template. Let's go to the console. I'm already under the Compute Engine. I use the left menu to click Compute Engine, and now I will go to the Instances Templates page. I will click Create Instance Template. To make this demonstration simpler, I will accept most of the defaults, especially the recommended ones. I will accept the machine type. I will accept the boot disk. This is using a public image to create the boot disk. I will check to allow HTTP traffic because I will install Apache Web Server in this virtual machines created by this instance template. And then I will click Open the Advanced Options, go to the Management section, scroll down to find the Automation fields, and then I will paste the startup script here. The startup script is basically updating the system package, apt updates, installing the Apache web server, and then it replaces the index.html default file with a bare minimum HTML file just to customize the web page. With that done, I can click Create to create the instance template. The template is ready, and you can use it to create identical virtual machines. The creation of virtual machines using instance templates will be demonstrated in another lab. The instance templates are used for automating the creation of virtual machines. Let's think of a web server application. If we have a fixed number of servers to respond to the average demand, when the amount of user requests increases, the system will not be able to respond to all requests. This is bad for business. On the other hand, if we have a fixed number of servers to respond to the peak demand, they will work most of the time at low utilization. This means unneeded costs. To solve this issue, we should use a technology that monitors, for instance, the server utilization, and when it exceeds a threshold, for instance, 70% of its capacity, a new virtual machine is added to the pool of web servers. Please refer to the bootcamp content and to the documentation about auto-scaling groups to learn how they work and the different types of load balancers that can be used with groups of virtual machines. I will open another tab here in the browser and visit cloud.google.com again. Now I will use the search functionality and enter auto-scaling group. I will open the first link. I will not explain auto-scaling in this demonstration, but you should read the documentation to understand and learn more about auto-scaling. You can see here that auto-scaling can be based on CPU utilization, load balancing serving capacity, and cloud monitoring metrics. As the auto-scaling group monitors the server metrics, for instance, CPU utilization, and let's say we have 5 servers in a group and they are almost reaching that limit utilization of the threshold. If one of those servers fails and go offline, the others will need to take care of the demand, and then their utilization will increase. When their utilization increases, it will trigger the auto-scaling to create a new virtual machine to add to the pool so the utilization is kept under the threshold. I will close this tab and go back to the demonstration. Now, let's say our web server is in production and using the auto-scaling group to add more virtual machines when the demand increases. Let's say that Apache released a new version of the Apache web server. The next virtual machine created using that instance template will update the system packages and install the new version of the Apache web server. That could be an issue. In a production environment, before applying any software updates, it must be tested in a controlled environment to make sure the update doesn't break the applications or create any unexpected behavior. Only after the update is tested and approved, it is applied to the production servers. This means that using a startup script in an instance template, as I did before, is a risk for the business. There must be or there could be scenarios or use cases that would need an instance template with a startup script to be used, but in general, it should be avoided. To avoid that kind of risk, you should create deterministic templates. I will switch to the documentation page again and click here on deterministic instance templates. On the first paragraph, the second statement starts with deterministic instance templates make explicitly clear the type of third-party services or apps to install on your instances when the instance template is deployed. By creating deterministic instance templates, you minimize ambiguity and unexpected behavior from your instance templates. And here, the section Why Create Deterministic Instance Templates states, in general, we recommend that the properties of your instance templates be as explicit and deterministic as possible. If you employ startup scripts in your instance templates that install or use third-party services, make sure that these scripts provide explicit information, such as the version of app to install. Compute engine can only rely on information defined in the template and has no control over referenced third-party services. If your template is too vague, your instance template might behave unexpectedly. Here we have one non-deterministic code sample. This is using the G-Cloud command line tool to create, compute instance templates. And what we can see here is the family of the operating system used. And here under the startup script part, it's using sudo apt install Apache 2 and is using the secure copy protocol from a remote machine with this IP address to copy the index.php from that machine or from that server. This index.php will be used in the instances created by using this instance template. Now I will scroll down to show the equivalent code, but more deterministic. Here is an equivalent sample code for that one, and the name of the startup, the name of the instances created with this instance template has sort of a versioning, and the Apache web server application to be installed using the apt install command has one specific version. So every virtual machine will install the same version of the Apache web server. Also, the index.php file that will be copied from a remote server will also have a versioning system. So every application installed or copied from a remote server will have one specific version. So all instances or virtual machines created by using this instance template would use the same versions of the softwares. Here, just above, there is a paragraph about create a custom image. And it says, create a custom image to use as the image for the template. This is preferable to startup scripts because it guarantees that every instance is the same. Startup scripts might have different results after distribution package updates. Use startup scripts in your instance templates for prototyping and rapid development, and use custom images when you are ready to deploy production quality services. Creating a custom image is like cloning the boot disk of the virtual machine. To use the custom image to create virtual machines, you need to create an instance template and set the machine type, the network and subnets, etc. The advantage of creating an instance template with a custom image is full control over the virtual machine settings. Another alternative to clone an existing virtual machine disk is to create an instance template from an existing virtual machine. The instance template inherits the machine type, the network settings, the virtual machine metadata, and so forth. It is basically a clone of the original virtual machine. The advantage in this case, it saves time when creating virtual machines and reduces configuration errors. I will go back again to the Google console and I will click Create Instance Template. As I did before, I will accept most of the defaults, but I need to change the boot disk, and I will click here the Change button. And instead of using a public image, this time I will select Custom Images. and select the image I want to use. In a previous lab, I created this custom Apache web server image. If you want to see how to create a custom image, please refer to that demonstration. I will accept the remaining options and click Select. I will scroll down and allow HTTP traffic again. The virtual machines created using this instance template, they will have Apache web server installed. That's why I need to allow the HTTP traffic. Reminding everyone that HTTP is not secure. In a production environment, you make sure you use HTTPS traffic. After allowing the HTTP traffic, I will click Create. I will hit refresh. And now I have two instance templates. One was created using a public image plus a startup script. And the second one was created using a custom image. The advantage of the second one is that all virtual machines created using this instance template will have the same versions of the softwares installed on it. In another lab, I will demonstrate how to use instance templates to create virtual machines. In this lab, I demonstrated how to create an instance template using a public image and a startup script, and I have also emphasized the importance of creating a deterministic instance template. Finally, I demonstrated how to create an instance template using a custom image. Thank you for watching.
Hello, and we are back. So far, we have demonstrated how to create a custom image and how to create instance templates to automate the creation of virtual machines, so we can create many virtual machines for the same purpose, for the same responsibility. What we will see after is how to use the instance templates to create virtual machines and how to create groups of virtual machines or manage instance groups. And once we have managed instance groups, how we can use auto-scaling to increase and decrease the number of virtual machines on that group based on the demand. Should we go to the next lab, Chris?
Hello. In this lab, I will demonstrate how to create virtual machines using instance templates. I will start opening a new tab and visiting cloud.google.com, and I will use the search bar and enter the following keywords: create a VM from an instance template. I will select the first link here. Here is the page about creating a virtual machine from an instance template. I will not go over all the content of the page. I will go straight to the steps required to create a virtual machine instance from an instance template. We have just a few steps. The first one is to go to the console and switch to the create an instance page. Then I will use the create VM from button or option to select to use instance templates to create the virtual machine. And then in the create VM from template window, select the template and then click create to create the virtual machine. I will go then to the console, and since I'm already in the VM instances page, I will click create instance. Here at the top, we have the create VM from button or option. I will click this button and select instance templates. This opens the list of instance templates available to use. And right now I cannot differentiate which one is using a public image with a startup script and which one is using a custom image. I will pause this step for now, and I will need to close here first. And then I will switch to the instance templates window, or right click to open the instance templates window in a new tab. Switch to that tab. And then here I see 324 is the one with the custom image, while 807 is the one with the public image and a startup script. I will use first the 324 to create a virtual machine instance. I will close this tab and then click the Create VM from option again, select Instance Templates, and now select the 324 to use the instance template with a custom image. Then I will click the Create button to create the virtual machine. The virtual machine is being created, and once it has a public IP or external IP address, I will copy that address, open a new tab, paste the address here, and check if I can reach the web server. It should show a customized web page, a very minimum web page that I customized when creating the custom image. This should show the minimum HTML customized page I used when creating the custom image. I will leave this tab there, and I will demonstrate now how to create a virtual machine with overrides. If I go back to the documentation, is the topic just below that one, and where or how you can customize the creation of the virtual machines even while using instance templates. I will click Create Instance again. Click Create VM from button, select Instance Templates. Now I will select the instance template ending with 807, which is the one I created using a public image plus a startup script. I will then click Customize. Here, you can customize different options of the virtual machine, and I will go to the Advanced tab, and here is the automation script, the startup script I used to create that instance template with a startup script. I will select all the content here and delete it, because I want to add a new startup script here that is different from the one used before. It is also a very minimal startup script, is a bash script, and I have some comments now to update the system package. I'm running the apt update-y command to install Apache Web Server apt install Apache 2-y command. And here now I have some commands to fetch data or metadata from the virtual machine. It's using the cur command to fetch some metadata from the virtual machine. The first one will store the name of the virtual machine on this variable VM_name, and there is another one to fetch the external IP address of the virtual machine and store in the external IP variable. Later, when creating the minimum index HTML file, I will use those variables to show hello from VM and then show the name of the virtual machine, and also to show the external IP address of that virtual machine. At the end of this script, I have a command, a system command, to restart the Apache web server. When everything is done about the startup script or the customization for this new virtual machine, I can click Create. The virtual machine is now being created. You can observe that it will take a little bit longer than the one created with a custom virtual machine, because this one will do all the customization, execute the startup script after the virtual machine is created. And the detail for this one is that each virtual machine that you create with the instance template should be equal. But in this case, I am customizing the settings of the virtual machine and using the instance template. So I am saving time because I'm using the instance template, but each virtual machine will be unique depending on the customizations, the manual customizations I do when creating the virtual machine with the customize option, even using an instance template. I will click the IP address of the virtual machine. I will copy the external IP of the virtual machine, open a new tab, paste the IP address here. It shows the customized index.html file I have using the latest startup script. I will close these tabs. And since I created those virtual machines just to demonstrate, I will select them all and hit delete to remove them from my project and avoid any costs. In this lab, I demonstrated how to create a virtual machine using an instance template. And I also demonstrated how to create a virtual machine using an instance template, but customizing some aspects of the virtual machine created. Thank you for watching, and see you in the next lab.
Okay, we are back. What we're going to do is, I think we have 2 more labs left. Is that if that's correct? And then we're going to go back and have 2 lectures on containers, which I always think is fun. But I wanted to remind everyone that we have a webinar on Thursday on how to become an architect. Please join us. We'll go over the role. We'll talk about what we do. We'll talk about the things that you need to do to get hired when you don't have any experience, because you can. You just have to have a certain set of characteristics, and we'll talk about what those characteristics actually are. And it's free, and I'll answer any questions you may have about your career. So my team will drop a link to that. I also wanted to let you know that if you just joined, lots of times YouTube sends people notifications at all kinds of times. We have the first week, my team will drop the playlist you can view. But we also have a completely free guide, a study guide for the Google Professional Cloud Architect exam that you can also sign up for, and it will be emailed to you. So please go check that out. My team will also drop that in the chat box. And if you've got some questions, let Leo and I know. Leo, what's coming next from your next 2 labs?
Next, I will demonstrate how to use that instance template to create a managed instance group, and then how to use auto-scaling on that group of virtual machines.
Sounds great. All right, Chris, let's start Leo's labs.
Hello. In this lab, I will demonstrate how to create a managed instance group. A managed instance group is a group of virtual machines that you control as a single entity. Managed instance groups support features such as auto-healing, auto-scaling, load balancing, multiple zone coverage, and stateful workloads. I will start here at this page, cloud.google.com, and I will click Docs to open Google Cloud documentation. And here from the left side menu, I will click Compute, then Virtual Machines, and lastly, I will click Compute Engine. Here is the documentation about the Compute Engine. We recommend you read the documentation to learn about the services you are going to use. From the documentation resources, one of the guides is Choose a Deployment Strategy. I will click this link to open this document, and then I will scroll down to the Review the available deployment options. This page shows and explains the different deployment options, but the focus of this demonstration is the Managed Instance Group, and it says a Managed Instance Group is a group of identical or similarly configured instances that you provision by using an instance template. You can make a Managed Instance Group stateful so that specific disks or metadata are preserved. For a stateless managed instance group, you can enable auto-scaling and configure a scaling policy. This means that if you want to use auto-scaling, then you need to use a stateless managed instance group. I will keep scrolling down. You can cover this document on your own time. I will not explain all the details from this document, but I will go to the What's Next session. And among the options, there is one to create a managed instance group. I will click this link to open the document. And here, under the basic scenarios for creating a managed instance group, there are different guides here. I will click the first one, Create a Managed Instance Group with Virtual Machines in a Single Zone, what is called Zonal Managed Instance Group. Now I have the Create a Managed Instance Group in a Single Zone document open, and I will go to the steps needed to create a Managed Instance Group in a Single Zone. There are quite a few steps, but the first one is to go to the Google Cloud Console and select the Instance Groups page. After that, click Create Instance Group. That will start the window to configure the instance group with the different settings and options. I will then go to the Google Console. Since I don't have the Google Console open, I will right-click Console and then open in a new tab. I will switch to that page and open the left side menu, Compute Engine, Instance Groups. I will click the button Create Instance Group. Here on the Create Instance Group page, we have different options on the left side. We have a new managed instance group for stateless virtual machines, another one for stateful virtual machines, and a new unmanaged instance group. Since I want to create a managed instance group with auto-scaling enabled, I need to select the stateless, the first one. Here, for the options, I will accept most of the defaults. but I need to select an instance template. I will use the instance template I created from or using a custom image which has Apache Web Server installed with a minimal index HTML file or customized file just saying hello. Scrolling down, I will reach the auto-scaling section, and after opening the combo selection box here, I can see different options. Off, do not auto-scale, scale out, only add instances to the group, never remove instances, and I can set auto-scaling to on, add and remove instances to the group. Depending on the use case you have at hand, a different selection will apply. For this demonstration, I will choose the option on to add and remove instances to the group. I will accept the minimum number of instances as 1 and maximum as 10. And also I will accept the CPU utilization as 60%. Continue scrolling down, we will reach a Show Advanced Configuration, and here you can find what is a standby pool. This means you would create or you would set the manage instance group to create virtual machines and have them on suspended state, ready to be resumed whenever the auto-scaling is triggered to add more virtual machines to the group. This means the virtual machines will be ready quicker than if the auto-scaling had to create the virtual machines and then add them to the group. With this option set, I will click Create to create the Manage Instance group with auto-scaling enabled. I will select the Compute Engine VM instances. I will right-click to open in a new tab to observe the virtual machines that will be created by the instance group. Here, we already have one virtual machine being created. It already has an external IP address. I will copy this IP address, open a new tab, paste the IP address here, and try to reach the web server that exists in that virtual machine. And the page says, hello world, this is the landing page of my Apache web server page. This is what I have customized in the custom image that is used by the instance template to create the manage instance group. And here we can see the characteristics or information about the manage instance group. Right now it has one instance. It is a group type, a manage group type. And we have here the auto-scaling settings to on with target CPU utilization at 60%. Now I will go to the VM instances page, and I will wait for the virtual machine is completely ready so I can SSH into that virtual machine. I will bring the SSH window up here. I will authorize the SSH window. And I will drag the SSH window to the side, and I will click the observability tab here on the VM instances page to show some metrics, and I will choose CPU, and I will click this button to enable auto refresh. I will also select the last 15 minutes to be shown on the screen. I will bring back the SSH window, and now I will update the system on the virtual machine. And when that's finished, I will install an application called Stress. This application will be used to simulate a higher CPU utilization on the virtual machine, kind of a stress test on the virtual machine. So the higher CPU utilization can trigger the auto-scaling group to add more virtual machines to the managed instance group. The application finished installing, and I will type in the command stress --CPU. 2 virtual CPUs will be stress tests --timeout 30 seconds. I will hit enter and switch to the metrics window. I will just move out and in again to see the utilization going up, and then at some point the number of virtual machines will also increase because the auto-scaling group will trigger the creation and addition of new virtual machines to this group. Now we have a second virtual machine being added and becoming available. And now we have a third virtual machine also being added to the group. The existing one was the 129. I will get the IP address of this one, that is 120, and also test to see if I can reach the web server is there. And the last one is also there. So at this moment, I have 3 virtual machines running in this managed instance group. And this number reflects here on the details of the managed instance group. I will go back to the documentation now, and I will scroll all the way to the bottom, and under the What's Next session, there is one link to enable auto-scaling to automatically add or delete virtual machines from your managed instance group based on increases or decreases in load. And in this document, I want to explain or to comment one of the sections that is called stabilization period. This document informs that since the metrics, CPU utilization, load balancing utilization, since those metrics usually vary a lot in time, they increase, they decrease all the time, having new virtual machines being added and removed all the time will not be practical or feasible. When the CPU utilization increases, new virtual machines are added to the managed instance group. But when the demand decreases, when the CPU utilization reduces, the auto-scaling group will wait for the time for this stabilization period. If no other peak in CPU utilization happens within a 10-minute period, the virtual machines will be reduced. But if in the period of 10 minutes another peak happens, then a new stabilization period will start. The stabilization period is equal to 10 minutes or initialization period that you set for the instance template, whichever is longer. And the stabilization period is used only for scale-in decisions when the auto-scaling has to delete virtual machines. I will keep scrolling down. And here under limitations, we have some limitations of using auto-scaling. It says you cannot use auto-scaling with the following instance groups, which don't allow the autoscaler to create or delete virtual machines according to demand. The first one that you cannot use autoscaling with is an unmanaged instance group. You also cannot use autoscaling with managed instance groups with stateful configuration. Also, with managed instance groups with virtual machine repair turned off. Regional managed instance groups with a target distribution shape of any or any single zone. And you cannot create virtual machine instances with specific names while autoscaling is turned on. The last item of the limitations informs: do not use compute engine autoscaling with managed instance groups that are owned by Google Kubernetes engine. For Google Kubernetes engine groups, use cluster autoscaling instead. After reading the documentation, I will go back to the virtual machine instances page, and we have 3 virtual machines working. I will refresh the pages that are accessing their web servers, and all of them are still running and responding to the requests from the web browser. I will wait for the 10 minutes to pass. So after the 10 minutes, the autoscaling group reduces the number of virtual machines present in the managed instance group. We can see the utilization has reduced. So the time, the stabilization period is being counted. And when the stabilization period is over, the virtual machines will be reduced and only one will remain, because this is the minimum set when creating the managed instance group. I'll hit refresh to check if the virtual machines have been removed. And yes, now we have only one virtual machine running. And if we try to refresh the web page they were serving, 2 of them will time out. Let's see. And checking the instance group, it will show one instance only. So after the stabilization period, the virtual machines were removed because there was only one peak in CPU utilization. Since no other CPU utilization peaks occurred in the stabilization period, the virtual machines are removed from the managed instance group. And here the first one timed out, and here the second one also timed out, and only one keeps working because the virtual machine still exists. Now we have one virtual machine running that was created by that managed instance group, and we have the instance group here. Whenever you don't want the virtual machines anymore, you can delete the whole instance group, and it will take care of deleting the virtual machines as well. So I selected the instance group here, and I will click delete to completely delete the instance group with the virtual machines. It requires to confirm that I want to delete. I typed delete, and then I press the delete button. Let me refresh the virtual machines page as well. After some time, the virtual machine disappeared. And if I switch to the instance groups page and refresh it, after some time, the instance group is also deleted. So right now, we don't have any instance groups and we don't have any virtual machines. In this lab, I demonstrated how to create a managed instance group with auto-scaling enabled. Thank you for watching and see you in the next lab.
Okay, we are back. We've got one more lab, but it looked like one question came in from Sergio. So I think we'll answer Sergio's question, see if any other questions came in, and then we'll get back to Leo's lab and then the next content. So Chris, if you want to bring in Sergio's question. Sergio says, hi, Mike. You said that a container could be hacked and could jump to another container or container runtime. Could I explain how these containers, and talk about the front end being exposed or not front end being exposed. Sergio, all this can occur without the front end even being exposed. And let me give you a couple of examples of the technology, its limitations, and therefore what some people actually do in super high security environments. Now, you may notice that the US government, for example, does not use the same cloud that regular people use. They asked for a separate cloud to be built for them for this particular reason. But that doesn't mean that a normal cloud isn't safe. So let's look at the real reality of where we're going into one of these environments. And let's take a cloud provider server or one of our servers, for example, while we're at it. So let me go to this example. It looks like these slides are pretty much where they're supposed to be. So let's say this is a server at the cloud provider. And on that server at the cloud provider, they've got their runtime module. And this could happen in your own data center too. Now, and then you've got your containers. So this is customer A. Now, we'll put a couple of the customer A servers on this, customer A's container on this. Now we've got customer B. Now we've got customer C. And this shouldn't happen under normal circumstances. But just work on this assumption. So this thing has an IP address on it, this container. So if anything does actually, let's do this. So there's a couple ways this could be hacked. One is if the operating system itself is hacked on the server. If you hack this operating system, anything contained in this operating system can also be hacked. So this server is on a cloud provider. If the cloud provider itself gets hacked, they can get into that server. The operating system, you'd have to hack the server. So what would have to happen is, and it's not the easiest attack to execute, you're the customer or you're a hacker, it doesn't matter. From the customer, you're always inside this. You can always reach your systems from the internal IP address. So if customer A, maybe they did something silly on their system, got hacked through that system, and it was able to hack the runtime module, it could theoretically go into one of their containers or another container sitting on that same server, because they're all sitting on that same server. That's the concern. Now, sure, if this was exposed to the internet, or worse yet, somebody had a Bastion host out there, and from the Bastion host, you can go jump on the customer's network and then break out of that and go through. But so that's one option, but it shouldn't happen that often. But at the same time, let's just the virtualization attack, which is harder to execute. You still have the security risk. So this could be a hypervisor. And if it's possible to, and you could have virtual machines from 2 servers for the same customer. So this could be customer A, and this could be customer B, all on the same server. So if this is a virtual machine, it's pretty hard to go from here to here, because these things are typically going to be on different subnets. In order to hack the hypervisor, you're going to have to escape the entire operating system itself, which should be really hard to do, and then hack into the hypervisor, and then escape the hypervisor back into this system, which is going to have a different IP, which is going to be very hard to do. But what do customers do when they can't handle other people's things on their servers? They basically get a dedicated host, which is not the same as a dedicated server. But in many cases, what they'll do is they'll get a dedicated host, and that host will have the cloud provider's hypervisor, and they will only put the cloud one customer's virtual machines on that. Now, you could also, if you wanted to, buy a dedicated hardware, and instead of taking the cloud provider's hypervisor, you could use Nutanix or VMware or something like that, and that you could put on your servers, and you could have the same Nutanix control plane in your data center and cloud. But that's the key: is with a virtual machine, you'd have to escape the virtual machine, escape the hypervisor, and go back. With the container, it's easier theoretically, because you would leave one container either through the container runtime module, or you'd hack the operating system. So theoretically, that's why virtual machines are more secure. Now, obviously, if they're exposed to the internet, that's even there, but you still have access to the private IP addresses of your system. So, and all this stuff could happen from a private network to a private network. Hope that helps there, Sergio. But it's not likely to really execute too many of these hacks. These are just the architectural considerations we face as cloud architect, cloud security architects, and any architect for that matter. All right, we've got a lab and then a lecture. Leo, what's your next lab on?
The next lab is how to create managed instance groups from an existing virtual machine.
Sounds great. Give me a hashtag Google Professional Cloud Architect, and let's roll with the content.
Hello. In this lab, I will demonstrate how to create a managed instance group from an existing virtual machine. I already have a virtual machine here. This virtual machine was created to be a web server. I used a custom image to create this virtual machine. Just to test it, I will copy the external IP address of this virtual machine, open a new tab here, paste the IP address and press enter. It should show the customized minimum web page from that web server. It shows hello world. So the virtual machine is working as a minimum web server. Please note, this is not for production, it's just for learning purposes. I will go back to the page cloud.google.com and I will use the search functionality. I will enter create a mic from an existing VM. And the first link is create a managed instance group from an existing virtual machine. I will click this link to open the document. And as usual, we recommend you read the documentation to learn more about the services you are going to use. There are some steps before you even begin. There are limitations you need to know when creating a managed instance group from an existing virtual machine. And here are the steps to create a managed instance group from an existing virtual machine. The first step is to visit the Google Cloud Virtual Machine Instances page and then select the name or select the virtual machine that I want to use to create a managed instance group. Here is the virtual machine I already have tested. I will select this virtual machine. So it shows the create a group based on this virtual machine option. I click that option. And then here there are some suggested steps. For instance, the name of the instance template that will be created to create the managed instance group. I will accept the suggested name. Regarding the disk, the default value is to generate a new image from the disk from the existing virtual machine. I will click the Edit Boot Disk option here, select a custom image, and select the custom Apache Web Server image. It's the same one I used to create the existing virtual machine. After that, I will click the Select button. Scrolling down the page, there are some settings for the instance group properties. I will accept the instance group name, the location as a single zone. Please read the documentation to learn more about the difference when using single zones and multiple zones. And I will click the Configure Instance Group button to open more options for customization of the managed instance group that I want to create from an existing virtual machine. I will accept the name, the location, but I will click the Configure Auto-Scaling button to configure how this managed instance group will behave regarding auto-scaling. I will accept the auto-scaling mode set to on. There are different modes here. I will not explain all of them, but the auto-scaling mode on means the auto-scaling will add virtual machines when needed and will remove virtual machines when they are not needed anymore based on the current demand or number of requests. I will accept the defaults as 1 for minimum number of instances and 10 for maximum number of instances inside this managed instance group. I will also accept the CPU utilization target or threshold as 60%. Any virtual machine that goes beyond the 60% threshold will trigger the creation of a new virtual machine. So the load on all instances in the managed instance group is below the threshold. With all set, I will click Done. And then I will click Create Group. Now the instance group is created. And if I go to the virtual machine instances page, it will show a new virtual machine was created for the instance group 1. The documentation emphasizes that the existing virtual machine that is used to create the managed instance group is not included as part of that group. Once you have created the group based on that existing virtual machine, you can turn it off, you can delete it, you can do whatever you need to do with that virtual machine, since it will not be part of this managed instance group. Just to test the virtual machine created in this lab, I will copy the external IP address, open a new tab, paste the IP address and press enter to verify if the web server shows hello world, and it does. We verify that the created virtual machine is working, and whenever the CPU utilization reaches the threshold of 60% for this virtual machine, the managed instance group will automatically create new virtual machines to keep the CPU utilization below the threshold. The cleanup part is based on the instance group page. You select the instance group and then you click delete, and you need to type in delete and press the delete button to confirm you want to delete the instance group. Now the instance group is deleted. There are no more instance groups. And let's go to the VM instances page and refresh. The virtual machine that was created with the manage instance group is deleted as well. So deleting the manage instance group will delete all virtual machines that were created when creating that manage instance group. The only virtual machine remaining is the existing virtual machine that was used to create that manage instance group. In this lab, I demonstrated how to create a manage instance group from an existing virtual machine. I also demonstrated how to remove all the virtual machines by deleting the manage instance group. Thank you for watching and see you in the next lab.
Okay, Leo and I are back. We've got a little bit of container content to go. We know we're working aggressively. We're going to try and finish up on Thursday, if at all possible, so that you can have Friday off. And then if you want next weekend, maybe you prepare for the exam. It's a pretty straightforward exam or something like that. Or watch it a second time or a third time or whatever. So we've got one more to go. Give me a hashtag Google Professional Cloud Architect. And Chris, let's get back to this content. In this next section, where we're going to prepare you for the Google Cloud Certified Google Professional Cloud Architect exam, we're going to cover storage, databases, data analytics, and observability. We're going to start with storage. So what is cloud storage? Storage is where you store your information. And well, there's lots of types of storage. I mean, we introduced them earlier: block storage, object storage, and file storage. We also talked about their use cases, but we'll go over it a little more here. But storage is where you store your data. So, for example, a business may have data. It will put it in one form of storage based upon how the storage needs to be used. Of course, if we're dealing with a virtual machine, which is going to use block storage, we have storage related to the data on that virtual machine. But there'll also be storage that's taken up on that virtual machine for the applications and the operating system as well. But they could be on different volumes, or example, which are like virtual drives. But keep that in the back of your mind, is storage is where you keep things. And cloud storage is where you keep your things on the cloud. Now, in Google world, cloud storage typically means object storage, but we'll talk about storage in general, and then we'll talk about the types of storage. So the point is you need to store your information somewhere. And that's what we're going to talk about. In this case, we're going to start with object storage. And object storage is a form of storage. Let's map it out. And the key with object storage is it's not like normal storage at all. It's much, much, much more like a database. And we're going to walk through this so you understand what is object storage and, for the most part, how it works. So if this is our RAID array that actually has the storage and underlying infrastructure, this thing is going to be a server, and it's just going to be full of hard drives. And they'll be in a RAID environment to increase speed, availability. And that's, well, I meant to draw hard drives, but that's what we're normally going to get. So that's the actual physical object storage. And they're going to be servers with a whole lot of hard drives. But the way object storage is going to work for us is, let's say we create a bucket, which is our virtual storage area, if you will. And all the providers use different terms. It doesn't matter how we call it. We have data over here. And let's say this data is, Cindy's Excel sheet, Cindy.xls. So if this is Cindy's spreadsheet. Now, when this actually gets written into or saved in object storage, what you're going to see is still going to look like Cindy XLS, but the data is actually going to be stored as an object. So as far as the object storage notice, this Cindy XLS is an object. And everything that puts in here will be individual objects. So if Cindy, for example, took a photo, and let's say it's Cindy.jpg, JPG, it's still going to be a different object, and it'll have a different object number, and it's going to have different information about that object.
So the first thing is when data is stored in object storage, it becomes an object. The second thing I want you to know is metadata. Metadata is data about the data. So Cindy.xls could have a lot of information about what's in that Excel spreadsheet, for example. Where the metadata could really tell you what's going on with that Cindy.jpg. So we can if we need to search for something, we can find it because this stuff is has metadata that we can search through. So a lot of good comes from that metadata. Now we also have to understand that this is flat storage, and what I mean by flat storage is it's not hierarchical like you would actually deal with in traditional storage. So you might have you might be used to the root of the drive. In file storage, for example, and underneath the root, you may have something like users, and underneath the users, you could have like, Mike, for example, and it all falls underneath each other. In object storage, it's really just flat storage. But what happens is when Cindy actually drops off her Excel spreadsheet, in this case, there's going to be a pointer to the data that's going to say, reach the data here. And the pointer to the data is going to be stored in very much like a database type format. And that's going to be how the data is actually accessed. So we may create things to make it look and feel hierarchical, but that's for us. It's a big, giant, flat storage environment with a pointer to the data. Now, the last thing we need to really remember with object storage is it's worm storage, or read once and write once and read many times. And here's the reason. In traditional object storage, the Cindy.xls cannot be changed. So if Cindy were to make just 0.1% difference, it would be a Cindy XLS, say, object, and it'll have a different object identifier. And then if she touches or removes it and manipulates it even one bit, it's going to create a new version. And because of that, the way object storage works like that, you can't really use it for a hard drive in most cases unless you're doing some kind of a storage gateway or to translate it, because this is different kind of storage. Imagine a swap file on a computer that had 4 terabytes of DRAM. That's the virtual RAM that you would use the hard drive for if you ran out of RAM. So if you had 4 terabytes of DRAM, and that means your swap file would be 6 terabytes. And what if that thing changed 100,000 times in a minute, which it could on your computer? That would be filling up. Just imagine each one of those would be 6 terabytes. And every single time it changed, potentially 100,000 times a minute, there'd be a new 6 terabyte object. So this is write once, read many times. And that's why object storage is not used for virtual machines. It's used for backup and archival purposes, software distribution, static website hosting. So now let's go back and talk about cloud storage. So now you know that Google's cloud storage is object storage, which means it's basically the same thing as AWS S3 or Azure Blob. Now, all the manufacturers have slightly different feature sets from each other, but the technology we're talking about is the same. Object storage is a very critical form of storage in cloud computing. It enables the persistent saving and retrieval of something. So you may have a virtual machine and you have an image of it, and you store that in object storage, and it doesn't change when it's in object storage. So, we may be using object storage, for example, for backups, and that's the reason why. Now, when we talk about cloud storage, when we talk about object storage, you may recall I talked about metadata on the data or data about the data. So for this reason, to be able to get data about the data, you often see object storage used in big data environments and data lakes because of the way object storage is structured. Object storage is incredible for backup, and it's typically good for analytics because of all the metadata that we can be collecting. So Google Cloud Storage is going to be scalable because the capacity is just there. You just need to use it. And it's designed to be what's called durable. And in addition to be relatively high availability. So the difference between availability and durability is as follows. Availability means, is it there when I need it? And you could have a 99.99% availability, means that system's available to you upwards and you can tolerate about 50 minutes of downtime per year, but otherwise it would be up and operational. Now, Imagine that your system's not operational for 52 minutes, but your data stayed. It was durable and nothing changed when you couldn't access it. So that's what we mean by durability. Availability is related to the systems being there when you need it. So if you want to think about that, how does the cloud provider do this? They take your data and they replicate it to other regions. Now, this means, if you've got a data center here, they moved it to another geographic area in another data center. So that means durability, which is wonderful. But what if you're in an environment where you have to provide what's called data sovereignty, where your data can't be copied to another region that's in another country or part of the world? So this is one of the things we have to think about when we deal with the SLAs and the contracts going back and forth to the cloud providers and even the cloud services we use, what we can use and when we cannot use it. But that's a much bigger topic. But if you were taking like a CISSP or a CCSP, it would be covered because it's critical there. And obviously it's something we teach to our security architects, but it's way above this type of certification. So we talked about what this is. So that is your object storage. Now, I want to talk about block storage, which we're going to have in the Google Cloud. And that's going to be what Google calls persistent disks. But the real reason is it's just block storage. So we can map that out in a minute. We can go look at what that would be for you. And I hope that it actually makes sense. So let's say we have your notebook computer. Let's say for right now, this is your notebook. And the reason I want to show this to you. Now your notebook inside of it has a hard drive. Probably an NVMe hard drive if you bought anything modern or real, because it's super fast and they're super tiny, which means they don't take up a lot of space. So they're really ideal for notebooks. They're great for that's what we use in high performance servers as well. But there is that. Now, when we store data over here on the hard drive, now this hard drive is file storage. And I'm sure you've looked, and let's say this is, I'll give you, let's say what a Windows machine would look like. I've not really used Windows machines for many years, and I recently bought one. So let's say this is the root of your drive. And then so we can call this C, if it's a C drive that you have. And then underneath that, you might have a folder called users. Trying to look at my computer to see what we'd have on a Windows machine. And then underneath the users, you got your username, which in my case would be Mike. And underneath that, we'll have folder versus folder versus folder. Now, the interesting thing to think about in this particular environment is this. When data is being stored to this drive, the way hard drives are typically designed is the data is written in little mini blocks. Now, this is file storage, but the data is actually written in little mini blocks. So this is a traditional way your computer would work. Now, since normally the data is written into blocks, let me introduce you to block storage. So the reason we have block storage is there's a limitation to how much storage we can put in a computer. So let's say this is a server. And let's say this server's got a lot of processing capacity. In a normal world where the storage limited to the server is limited to the number, oops, I don't know what I just did there, bear with me. The storage in the server would be limited to the number of hard drives in the server and the size of the hard drives of the server. But what if the server was mostly doing compute? Meaning heavy-duty calculations while it still store things. We don't want ever the storage and the server to be a limitation. So what we do in the modern data centers, and by modern data centers, I mean for the last couple of decades, what we do is this. We decouple the server environment from the storage environment. So what we have over here is something called the storage area network. And what is that? I can tell you right now. It's a big box, or they're server boxes, and they're full of hard drives. Now these could be NVMe hard drives, and that's going to be your fastest type of storage you would get in this environment. They could be old school magnetic hard drives, but let's just talk about this. So this is what you typically get in a storage area network. Now, because we have, because we have a network between these devices, and obviously there's going to be different routers and switches, but I'm just going to call this the network. And the storage area network is plugged into the network, and the server is now plugged into the network. And this is typical in a data center environment. Cloud provider, traditional data center, and here's why. I showed you how normally we save data in blocks on file storage. But block storage, and one of the greatest things about block storage is when we take data into a storage area network or a block storage environment, what ultimately happens is the data is written in a block. So that we have the data, and it's going to be written into a block or a group of blocks that are going to be pooled on this storage environment. So what block storage enables us to do is we can create a virtual hard drive that really speaks, so virtual HDD, and that virtual hard drive is really here, but we can mount that virtual hard drive to the server, and the server thinks it's a local hard drive because of the way data is normally written into blocks into a normal hard drive, and in the storage area network, they write the data into blocks, and it looks and feels a lot like the storage you traditionally had in the server. But it's not. First, this storage is accessed over a network, which means the network will be the limitation. If this server has a 10 gig Ethernet network card, there's no way then they could ever get faster than 10 gigs, no matter how fast the storage environment would be. So keep that in mind, that we've decoupled the servers and the storage, which is great from a scalability perspective, but we're not going to get anywhere near the same performance. And here's the other reason we're not going to get the same amount of performance. We have to think about the amount of network connections the NVM, this storage area network has, and it only is going to have so much capacity. But we have to remember that this block storage area network could be divided by 100 or 1,000 different cloud customers. And they're all sharing this bandwidth and the speed of this, which is why you can typically get much faster storage inside of the server itself than you ever can with block storage. I hope that makes sense. But in most cases, block storage will be the fastest storage we have in cloud computing. So block storage on Google is called a persistent disk. And there'll be various options you have for storing. And when it comes to storage, we have to think of IOPS and we have to think of throughput. So maybe I'll whiteboard that out for you so you can understand what we're talking about here. So IOPS refers to this: how many input and output operations you can do in a second here. So if we have more IOPS, we can write, and read more times per second. If this is, we can access this drive 1,000 times a second, then we can access this drive 1,000 times a second. And we can't access it more than that. So if we think about latency, how often you can actually go to the disk will determine your latency. So the higher your IOPS, or input and output operations per second, the lower your latency. Higher IOPS, lower latency. So that means there's an inverse correlation to IOPS and latency. Low IOPS, or low input and output operations per second, like an old school magnetic hard drive, high latency. So keep that in the back of your mind. Now, we also need to be considered with the throughput of our load. So let's say we had two vehicles that we were going to send from Palm Beach to New York City. Vehicle one is a tractor trailer, and it's a big truck with huge capacity. The other vehicle is a Lamborghini. I'm going to call it Lambo to save space. So now, which one has less time from 0 to 60? It's the Lamborghini. This vehicle has much lower latency to start up and access it. Now, which one has more throughput? Throughput is the amount of stuff that can be carried. So if we took the tractor trailer and then we took the Lamborghini and we said, I want you to go to New York as fast as you can, carry as much stuff as you can, and but at the end of the day, the winner is the person or the vehicle that brought more stuff. Who do you think that would win? The tractor trailer has much higher throughput. This thing can maybe hold 3 or 4 or 5 or 10 tons worth of weight. I think it's more than that. This Lamborghini may stop at a few hundred pounds of capacity, maybe 1,000 pounds of capacity, maybe 2 tons. I don't know, but it's not, or maybe a ton, but it's not going to be that much. So throughput is typically measured in megabit per second or gigabit per second. And latency, we typically think of higher IOPS means lower latency. And you'll have options of which of these you potentially could use. Now, when do you use which? When it's for object storage, we often use it, like I said, for backup, archival purposes, unstructured data like images, videos, backups, large data sets. The data is stored as an object. It includes the object, which includes the content, the metadata, and a unique identifier. That's that database pointer I was referring to, database-like pointer. So if you think about that, object storage is really great for anything that needs scalable, durable storage, and it can be accessed over an API, and that's one of the ways it's often accessed. So we have multiple options which we can talk about with regards to how redundant you want it to be, how you can manage your information, and potentially object storage can integrate into other Google services like BigQuery. Now, when we'll talk about file storage. File storage is just the standard kind of storage we normally use. It's what's in your hard drive. It's that hierarchical root, users, home, whatever, underneath that. But where would we use that in cloud computing? Well, where we use it in cloud computing is when we need multiple systems to be able to access the same thing. Let's say we have multiple servers that need to access the same content to give it to somebody else. This is where we use file storage. Because block storage, even though it's not, it's going to be local to the server because it's going to be like a virtual hard drive. But file storage itself, now that's different. That's shared amongst other users. So we often use these types of file storage. Google also has a managed file storage, their file storage they call File Store, and it's a fully managed file storage system. And that obviously integrates fairly easily with Compute Engine for virtual machines that can access it, Kubernetes. So traditional, what we're talking about, file storage accessed over and over. Now let's discuss the storage tiers you have with Google Cloud Storage, otherwise known as object storage. And Google has storage tiers just like any other cloud providers. And the storage tiers, as I mentioned, will be related to the availability and the performance. So let's walk down some of these stores. We have standard storage. Now this is the standard object storage offering given by Google Cloud. You can think of this as, say, AWS S3. It's Google's equivalent version of that platform. Now, this typically comes with some very good availability. In fact, with standard storage, we're talking about availability that's at least or greater than 99.99%, especially because with multi-region and dual-region environments, and 99% in all regions, or 99.99% in all regions. So this is good, relatively high available storage, and of course, it's also very highly durable, meaning if something were to happen and these systems were down, it's still going to be there. Now, we also have Nearline in the Google Cloud, and what we're dealing with Nearline is we pay less to put our data there. We typically get reduced availability, and the key with this for us to work is we really want to store our data here for at least 30 days, and that's going to be the minimum storage duration anyway. And the availability is reduced, and now it's 99.95 in multi-regions and dual region, and 99.9% available in regions. So we actually lost a big level of availability, because if you think of standard storage, we had 99.99% in regions. And when it comes down to nearline, it's 99.9. So big difference in availability. But this is not designed for data that you need to access all the time. It's data that you need to access intermittently for a period of time. And you pay less to store your data here, but you pay a retrieval fee. So if you think of nearline, and then you want to think of like AWS by comparison, this is S3 infrequent access. So now we can talk about Google cold line storage. Now here we're paying a lot less. We have to store our data here for at least 90 days. We're going to pay a retrieval fee for getting our data. And the availability is still really good here, or it's at least as good as nearline, in that it's 99.95% in multi-region and dual region deployments and 99.9% in regions. So we're still dealing with good availability, but it's designed for low cost, but you're not going to use it that often. You need to store your data for the same 90 days. And then we have the archive. And this is your longest term, lowest cost storage that you can possibly have, but you're going to pay retrieval fees to get it. So I hope this kind of helps. The last two are let's say different versions of AWS Glacier that we'd be talking about, but those are really your storage classes when we're actually talking about the Google Cloud for object storage. And I hope those classes make sense to you. So let's talk about lifecycle management. Lifecycle management of data is typically going to be moving your storage around to the things that make most sense for you. And you may do this for the reasons of you want to optimize your costs. So let me show you what lifecycle management could be. You might actively use your data periodically. So let's map it out. So let's say we have new data. And this new data we're going to frequently access for about 60 days. So while we're frequently accessing it, let's keep it. And let's keep it in the most performance-oriented standard type of we have. So let's keep it in standard. Now let's say that we use this data all the time for 60 days. And then after 60 days, we may only use this data 5-10 times that much. So here's where we're going to put it in that nearline storage. Access, low, and intermittent. And let's say we keep it here for 30 days. And we'll set up a policy that says keep data here for 60 days, then move to, nearline for 60 days. And then what if at that point we're not really going to need it very frequently, and we're not time sensitive when we actually need it, and we want to store it as low cost as possible? So maybe after 30 days, what we put is we put it in cold line. And we keep it here for a long period of time, maybe 6 months, maybe 9 months, maybe a year. And at some point when it needs to be archived, then we move it somewhere else. So that's the point of lifecycle management, is to move your data around so you're going to pay the least cost for your data and have it when you need it, but find ways to make it less inexpensive. So let's talk about encryption that you're getting in Google Cloud. By default, the data at rest is going to be encrypted with AES 256-bit encryption, which is the standard now for the most part for encrypting data. And data in transit or in movement will be encrypted with TLS type security. For users requiring additional control of encryption, Google does support customer-managed encryption keys and customer-supplied encryption keys. And this gives the ability for high-security environments to have a little more flexibility and any kind of compliance they need for sensitive security workloads. Now, we can talk about backups and snapshots. So, obviously, you want to back up your data, but you also want to snapshot your virtual machine. And that is going to make it very, very easy for you to go build back your system. Let me whiteboard it out for you. So let's say we have a virtual machine. I guess I should call it compute engine since it is a Google Professional Cloud Architect exam. But let's say we've got this VM. I'll call it compute engine. So let's say we've got this, and you'll recall that we always have block storage here. And that's going to be the virtual hard drive. So this is block storage, otherwise known. Google likes to call it Google likes to call it a persistent disk. So, we've got this virtual machine. What we can actually do is we can take this virtual machine and we can create a bit by bit image. And this bit identical image is going to be a bit by bit copy of that entire hard drive into an image type file. And just think of that. So if anything happens to this server, it goes away. All you do is you use this bit identical image and it will launch that identical server with every last amount of data on it, assuming it's every last amount of data, assuming you made an image of that drive that you have on it, and that's up and operational. This is, a snapshot. And you'll typically take these snapshots and they'll typically be stored on object storage. And this gives you the option. And you can also do versions of this and create versions of this. So we could actually keep the backup of this version from today, tomorrow, the next day, the next day, the next day, the next day. And we could do it more frequently than that if we wanted to keep our systems great. So that is a snapshot. Now, the snapshot's different than a backup. A backup is when we take the hard drive or the block storage drive, and then we basically back up whatever data we want on a frequently thing, and we send this to something. It could be this is backup. This could be object storage, which we often use. This could be a backup tape. This could be a backup hard drive, but we're backing up the data. The snapshot's a bit by bit identical thing, one thing, and it reconstitutes the whole thing. And this is copies of your data. So it's similar but different. The reality is you need both of these, typically speaking, in a high availability security environment. If we think storage has evolved quite a lot over time, early hard drives were huge and they stored less than a megabit a file. I remember having floppy disks, these 5 1/4 floppy disks. And I think if I remember correctly, they were 360K. And I think if I remember correctly, that was what we got out of them. But they didn't give us a whole lot of data either. And now I've got a 96 terabyte RAID array that sits right next to my computer. And it's only this big. It's kind of amazing to think about how we've grown so much. So keep that in the back of your mind. Now, when it comes to the cloud, they've already got all this storage that's actually ready for you. May cost more, may not. May cost a lot more, may not. And you'll have to figure that out for your business based upon your data needs and your data utilization patterns and where you store it. But understand that cloud does provide a lot. But also understand there's a lot of analytics that can be done on this data, especially the data that's stored as data storage. So let's think of the future of data here. Organizations have now determined that data is a critical asset. And for all the AI things people want to do, the only thing we can train our models on is data and quality data. When it comes to AI, if we feed it and train it on bad data, then the results are bad. If we feed it and train it on pristine data, then our AI systems are much more likely to do what we want. So we need to think about data. We see GPUs growing every single day in their capacity in terms of managing data. We see CPUs that are getting better at AI workloads. There are companies that make ASICs, which are little chips that can do various AI things super fast, much faster than a GPU in many cases, but it can very specific tasks that they can do. So we have to think about all of these things. And Google's cloud focus is going to be on big data. They're going to focus on databases. They're going to focus on analytics. They're going to focus on a lot of data security. And if you think about Google, when they talk about data, they've got a little bit of experience in here, right? They've got advertising, which has collected all kinds of data to be able to target your advertising, which people you're looking for, which part of the world, with which hobbies. I mean, there's all this data they've got. So keep that in the back of your mind. So let's discuss Google Cloud Storage a little more. We have the concept of bucket labels. Now that's what we're going to label our buckets, or where we're ultimately calling it. And what it's going to use is it's going to use a key value pair to actually label the buckets with other resources. And that'll help keep track of what these things are. So we might use bucket labels for data classification or team ownership or billing, and we can put up to 64 labels per bucket. So we're storing our data, and that's what I said. We've got a lot of information, a lot of labels, a lot of metadata on that label. Now, we also want to think about object naming and versioning. Anytime we deal with an object in object storage, the names have to be unique inside of a bucket, but not globally, which means I have to use the same things in, if I've got an object storage bucket, all those names need to be unique. But if I have a different bucket, I can use different names. Well, I hope that kind of makes sense to you. In a single folder, you wouldn't have two identical things that are, typically speaking, on your hard drive, and your hard drive wouldn't let you either overwrite the first one or ask you to change the name of the second version. But you could have two folders on your computer with the same name inside of each folder. So even though it's object storage, not file storage, it should be easy for you to remember. Object names must be unique inside of a bucket, but do not have to be globally. And with regards to object versioning, if we're using versioning, which normally object storage does by default, but the cloud providers may usually disable that by default, and then they give you the option to use versioning. And versioning means every time that file is touched or modified, it creates a new one and it stores the old ones for you. And by doing so, you've got access to many different copies. And that might be good sometimes. It might be costly, but it might be good. What if the entire team was working on something and the last version got corrupted? You can go back to the previous version. At least it gives you that. So good backups, all these things we want to do because we want to think about how do we keep our data as durable as possible. And versioning may help us even more. But the more versions we store, the greater our storage costs are. So it's an architectural trade-off. And what makes a good trade? The one that provides the business most of what it needs or is the best for the business after evaluating all trade-offs and the technology, the architectural solution, what have you. And we can, with regards to object lifecycle management, we can automate things. And we can automate deleting objects or changing storage classes based upon a condition like an age or a last access, or even the number of versions we have. Let's finish our discussion on storage. And now let's talk a little bit more about file store. As you recall, file store is Google managed a file sharing for you. And it uses something that's very similar to the NFS file system because it's basically file storage. It is just file storage. And because it's just like NFS, it's going to be what's called POSIX compatible. So if you need POSIX compatible storage, understand file store will give it to you. And you can use the last.d file to grow and shrink your clusters as needed, the amount of storage you actually have. And it's pretty good availability at 99.9%, for which, for a single file server, that would be, you'd get a little more than that, but it's not terrible for a single file server. And obviously, you can use more than one file server if you needed, and to use it to create your own high availability storage. But the reality is, for most people, 99.9% for file storage is going to be good enough. So I want to show you the difference between the way this works and what you would normally have to do. And then we're going to talk about how do you get your storage set up, what have you, and using the storage. So in a traditional environment, here's what we have to do to use file storage. So let's say we've got our server over here. And we've got our storage over here. These are our hard drives or our storage volumes or whatever. So let's just call this storage. What we have to do on a normal file server is we have to create a file share. And it could be a Windows SMB share. It could be an NFS share on a Linux machine or a Unix machine. And then what happens is other users or other servers that need to access the data, for example, can just access the data off of this NFS share. This is normally what we've been using for decades. And the only thing that you have to think of about this is, you have to manage this server and you have to manage this storage. Now, here's where things can get icky on this server. What happens when the server runs out of storage? What do? We either move to a bigger server that has greater capacity storage, or we create a different file share on another server. So out of the capacity thing here, we have to maintain the server, patch the operating system. It's not that big of a deal, but people, try to make it sound so much scarier than it is. It's not that big of a deal, but we'd have to manage the server, we'd have to manage our capacity planning, and we have to think about it. Now let's talk about what file store really is. Well, file store is basically Google has some type of device that's creating file sharing NFS like file storage. So in this case, you basically purchase your NFS file share for them, but it's called file store, and it's going to be very NFS like. And it's a managed service, so all you do is create your share, and all the underlying servers, all that make this possible, they're all managed by Google. Now, the other good thing that's kind of great is, generally speaking, file store isn't going to run out of capacity. So you can typically just use it and add more as you actually need it. So that is the advantage, the real advantage of the cloud. I mean, some people would say not managing the server is an advantage. It is, but it's not that much of an advantage. But not having to worry about your file storage running out of storage over here and not having to think about that is a big win here. Let's really think about this. So how do we deal with this? How do we create a Firestore instance? So what we do is we create a Firestore instance, and a single NFS share is going to be created with default Unix permissions. And the instances must be in the same project and VPC network as your compute engine would be, or your Kubernetes engine clients, or your containers has to be, unless you're going to use some form of a shared VPC. Now, the IP allocation that file store can automatically select an available IP address that'll work, but remember, it's going to be coming from a private IP address, RFC 1918 private addresses. So why don't you use something like this? You would use it when you need multiple devices that actually need access to the same data at the same time. You would use this anytime you would need to use file sharing, just like you used to use a file server. Now, I talked about block storage, and I talked about block storage being the virtual hard drives that we actually have. Now, we have to understand that block storage is going to be our best, but there are different flavors of block storage. Generally speaking, magnetic hard drives are a lot cheaper per gigabit or terabit than non-volatile memory express drives are. Now, NVMe drives are super fast and relatively low latency. Hard drives are not fast at all, and they have relatively high latency, but they're relatively cheap for storage. So when we choose a disk for our virtual machine, we have multiple options, and I want to talk about some of those options. We have performance persistent disk. Now, this is going to be the highest performance, meaning lowest latency storage we actually have. So what that means, the highest IOPS. It's going to be one of the highest we actually have. And this is going to mean lower latency, and it's going to be backed by hard drives that are going to be solid state drives. So this is going to be relatively good performance. Now, when we have a cheaper option, which is what's called the standard persistent disk. Now, this you could use. It's suitable for data processing workloads potentially that are not latency affected, and they typically use sequential input and output. Because remember, we're dealing with a hard drive that's going to be spinning, and if it's in a similar part of the drive, it's going to be easier to access and faster to access because the latency is going to be slow to like search across the entire hard drive. So standard persistent disk is going to be relatively inexpensive, but it's not going to give you any good level of performance at all. Now, you can ultimately run into the extreme persistent disk, and it says they're backed by solid state drives. They are, but they're probably backed by NVMe SSD drives. Now, these are designed for your databases that require low latency and a lot of input and output operations per second. It's going to be one of the fastest things you can actually get inside of Google Cloud. So large databases, for example, you might be wanting to do this. So, and then we also have this balanced persistence disk, and it's going to be backed by SSD, and it's going to be really an alternative to the performance persistent disk, and it's going to give us balance of performance and cost. So it'll be somewhere, it's going to give us for virtual machines, you might use it for except normal size virtual machines, not very big ones, because these disks have the same maximum number of IOPS as the SSD performance, but it's designed for general purpose applications. Let's discuss a little bit more about the persistent disk. And this is something really great about persistent disks in cloud computing, is that we can actually resize them. So let's say we thought we needed a 50 gigabyte persistent disk for a small server, and because it was doing very small things, wasn't going to be storing that much, and somehow it got filled up and we needed to change it to 500 gigabits. We can resize this, and we can resize this VM in the Cloud Console, which makes it easy to use. We can resize file systems using the resize 2FS or 2FS command that you typically on Linux, and that will enable you to scale to increase the size of your hard drive. So keep this in mind that they're virtually attached. Remember, over a network, they're not physically attached to the actual server. One thing to remember is we can resize up, making it bigger, the disk, but we can't resize the disk down. Now, obviously, the highest performance, the lowest latency storage that we're ever going to get is going to be local to that server itself. So we have the option at times of using the local SSD for certain things, but we have to remember that it's ephemeral, meaning that it goes away if we get rid of the instance or the virtual machine. But what's happening is it's using the SSDs that are attached to the server. So this gives us incredibly good performance. Very high IOPS, which means very low latency, typically very good throughput. Let's think about where we could use this. Where could we benefit from high performance storage and not have to worry about the data basically going away when we get rid of the virtual machine? So we have a caching environment, or we need a scratch processing space. That's the kind of use case where we could use the local SSD and get that maximum performance and not have to worry about the information being ephemeral. So remember, that's exactly what's in the system. So if we have high performance compute that we need to do with a local SSD, media rendering, for example, some kind of data analytics, cache, any kind of load thing that we're not worried about storing the data later, that's where the local SSD will make sense.
Okay, so Leo and I are going to wrap up for the day. So, just want to give you that kind of guidance. I think we had a pretty big day. We talked about a lot of things, lots of compute, got into a little bit of storage, and that's what we're going to finish for today. Now, Leo, I know you're going to have some more labs that are going to be coming up. And the next thing we're going to go on to tomorrow will be things a little more on storage, and then we're going to go into databases. What labs do you have coming up soon, Leo?
Tomorrow we have labs of how to attach a persistent disk to a virtual machine, how to create a bucket, a cloud storage bucket, and how to host a static website in a cloud storage bucket.
Sounds terrific. And I'm going to end with Rohit's question because it's a great question. Rohit asked how we can evaluate someone and let them know where they're at. So if you are a student of ours in our program, I'd let you know. For example, our students right now are working on an architecture. As soon as this boot camp's over, they'll be presenting the architecture back to us, giving us their RFP responses like they would in a real architecture, giving a presentation back to us, and we'll be able to evaluate them on their technical ability, their logic, the rationale behind their architectures, how well the business architecture and the technology architecture solve the problem, its relevance to the business, the presentation skills, the executive communication skills, and the CXO relevancy. And if I've got students that are ready, I can tell them right there, you're ready. Because we train our people in architecture and that's how we do it. But if you're not one of our students and if you want to see if you know, I am more than happy on any of our weekly free architecture webinars. After we talk about what we do and after we talk about the skills you need and after we talk about how to get hired, if you say, Mike, could you tell me if I'm ready to get an architecture job or ready to get a network engineering job or ready to get an enterprise architect job? I'll be able to give you 3 or 4 questions that'll show me in about 2 minutes whether you understand architecture and where your gaps are. Because I'll go to a business thing, I'll ask you a holistic thing that'll get your perspective of the whole architecture. I'll be able to see your ability to evaluate trade-offs. And I can say, all you need is this cert, or you need this training, or you need to do this. And I'm happy to do it, Rohit, and I do it completely free on our weekly webinar. So maybe come to the weekly webinar, learn what we do, learn the skills you do, and I would be honored to assist you in getting to your goals. Okay, Leo, we're going to say good night to everybody. I really gratefully you stuck around a little longer. We're going to try and finish Thursday night and give you Friday completely off, and we did a heck of a boot camp here. We got involved into a lot of stuff. We got far beyond the concepts in the boot camp, and Leo gave you lots of demonstrations. So if you haven't given us a video like, maybe give it a like. If you're not a subscriber, maybe subscribe and hit the bell. And then Leo and I will be back tomorrow. Anything to say, Leo? Okay, I think Leo was... Leo got a little cut off. Were you saying welcome back tomorrow? We look forward to see you. Is that what I was reading essentially?
That's correct.
All right. See you all tomorrow. Have a wonderful night and maybe give us a hashtag.